New Mexico. Watch the first atomic detonation in history. Operation Trinity. The long series of nuclear tests is underway. July 1946. Operation Crossroads. Bikini Atoll in the Mississippi. The war over, scientists and military personnel busied themselves setting up a targeted ship for the first peacetime test of the atomic bomb. High-ranking military personnel and civilian observers watched the able shot. 19 kilograms, burst 516 feet above the surface of the lagoon. Damage to the target array is assessed and preparations are underway for the Baker shot. The bomb, similar in type to the able test, is located in an airtight caisson beneath the surface of this tropical lagoon. With all preparations made, Baker shot occurs on schedule. Many impressive and startling effects were observed on this shot, including the first appearance of a base surge, seen here enveloping the target system. April 1948, Enowetok Atoll, Mississippi. Our third nuclear test program gets underway. Operation Sandstorm. 3 weapons, fired on 200-foot towers, with batteries of scientific instruments to record results. As a bikini, drone planes are used here. Giant planes, heavily instrumented but without crew, take off to fly through the heart of each atomic cloud, to collect samples of that cloud for detailed radiochemical analysis. Three times the sound and fury of atomic detonation shatter the Pacific dome. 3 times a scientific laboratory is created to study previously unattainable effects of high temperature and pressure. But what did we learn from these detonations? What were we trying to prove? Why did we expend this almost priceless nuclear material and these thousands of man-hours in space? Let the men of Los Alamos give us the answer.
We returned to the hill from the sandstone test with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, tip design, core arrangement, initiators. Information that would enable us to increase the small percentage of active material that actually burns during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive, the elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive force, and that the implosion principle was sound. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonation, the effects of the atomic explosion became of prime concern to the armed forces. Thus, Crossroads using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Eagle and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory material. Here we were able to utilize uranium-235 in an implosion-type weapon. As time went on, we had increased our knowledge of weapon design and had, therefore, increased joule per kilogram of active material. This is where we stood by the end of sandstone. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as J Division, is organized. Dr. Alvin C. Graves was selected to head this division, a unit with the specific job of testing weapons. By autumn of '48, a test program was framed. This calls for experimentation of new weapon designs with the objective of again moving our knowledge curve upward to a more effective level. Once more, we propose to better joule per kilogram investment. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon. These are the main objectives in the weapon development field.
And so Operation Greenhouse gets underway, with Enewetak designated a test program for specific proving grounds. Entity, run it, every rule of astronomy. During late 1950 and early 1951, work progressed in the island. Towers are built, recording stations are constructed. Coaxial cables to shock towers are laid. Myriads of instruments and intricate wiring hookups are checked and double-checked. Finally, everything is ready for the biggest job in nuclear testing, the job of obtaining exact information about the detonation itself. The builders are through, and the scientists take over the story.
Those of us from the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into two major areas: diagnostic testing and effective testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effect tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, 3 kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time, the rate at which the chain reaction multiplies, alpha measurement, and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HE system, is cabled down to a recording station and measured by sleep oscilloscopes. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between an impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomenon. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fission in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons. 1 kiloton being the force released in 1,000 tons of high explosive. One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield per fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shotgun. They will travel in a long arc and pass through the cloud at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself.
Shot number 1, jaw. The objective of the test of the Howe weapon was to prove a weapon of higher yield and efficiency than currently stockpiled. The predicted increase of efficiency made possible by the Type D test was confirmed. Shot number 2, easy. The objective of the test was to prove a lighter and smaller weapon with acceptable efficiency. The feasibility of obtaining acceptable efficiencies with lighter and smaller weapons was confirmed, and thereby future weapons design was advanced. Shot number 3, yours. A step was taken along the path to thermonuclear weapons by the achievement of a fusion reactor. Shot number 4, isotope. A successful booster reaction proved the feasibility of increasing fission yield by a limited fusion reaction and gave more impetus to the development of booster weapons. Fission weapons proof test. Physics experiments run on thermonuclear reactions. Military and civil defense knowledge immeasurably increased. This was the accomplishment at Grony, at Entity, at Eerie in the spring of 1951. Once more, the Pacific Proving Ground has proved its value, but the job is far from complete. Each test series leads inevitably to new developments requiring still more tests, more frequent than are practical at distance and a week on, where logistic problems make it difficult to run more than one test a year. We need a site much closer to home, a site in the continental United States. But where?
For a long time. As a matter of fact, ever since Trinity, men from Los Alamos had been eyeing the great barren stretches of the Southwest. This region, for the most part, fits the bill. Isolated from centers of population. favorable winds, with the necessary consistency of soil and formation of Earth's strata below. And so beyond the World War II training base, to the north of an early day Nevada stage stop called Indian Springs, 65 miles north and west of Las Vegas, an atomic range was set. A test site of over 400 square miles of flatbed valley, mingled with mountains of solid rock, whose veins once colored history with gold and silver. A range remote from civilization, isolated, forgotten as the names of the men who once made their fortunes. In the pre-dawn hours of January 1951, this long deserted countryside came once more into international focus with Operation Rain. The test of 5 atomic bombs. 5 successful airdrops that saved the weapons research program months of time, considerable money, and helped Bartholomew prove the radical new idea of small atomic bombs. Soon after Ranger, another use of the Nevada test site was apparent. This was a chance for the military to get more information in a shorter space of time on the effects of atomic weapons. Vital fact. For what good are atomic weapons without full knowledge of what they can really do, and how we can be protected against their effects?
Thus, Operation Buster was born. In the fall of 1951, the combined operation Buster Jangle was held at the Nevada Proving Ground. 5 weapons in Operation Buster, 1 on 100-foot tower and 4 airdrops. A tent city, Camp Desert Rock, was activated and occupied by observers from all of Earth, arriving here from all corners of the Earth to participate in an atomic maneuver. Here they received extensive indoctrination by experts from the Armed Forces Special Weapons Project in the expected phenomena of the detonation, and by Camp Desert Rock personnel on the assumed tactics of the maneuver. Early on shock morning, they load into trucks and buses for the long trip to the target area. In the target area, last-minute orientation talks are given, and the observers prepare themselves to watch an atomic detonation from the closest point that personnel have ever been during nuclear tests. Following the detonation, the troops move forward to the ground zero area to inspect the effects of the bomb. Operation Jangle, immediately following Buster, was our first test of surface and underground atomic detonation, designed to study military effects of these types of bursts. Jangle number 1, the surface jump, heavily instrumented to study energy coupling in the Earth itself. This low-lying cloud is hot with radioactivity trapped in Earth particles thrown out by the force of the explosion. In a little while, ground monitors mark off the outer limits of personnel re-entry into the blast site. In the fringes and interior of the crater itself, the spot that once was ground zero, there are soil specimens of great value if they can be collected before their short-lived radioactivity dies. Remote control Army units, drone units, are warming up for this collection job. A compact television camera mounted on the front of each weasel will inspect the terrain as they go and relay the pictures back to their guiding control station. Troops on the front of one drone will gouge out and bring back surface samples of the crater dirt. A drill rig mounted on the back of the other weasel will bore down and secure cores, which will tell the story of subsurface radioactivity. Now the push is on for Jangle 2, the underground detonation. Like the surface round, this will be a 1 kiloton gas, but this time it will be detonated 17 feet beneath the surface of the Nevada soil. Very extensive military effects tests will be run with this detonation. Dummy buildings, superimposed loads to represent upper floors, an underground structure, such as fuel storage tanks, water systems under hydrostatic pressure, gas mains, and electrical mains have been constructed to gain realistic data on ground shock and cratering action. Inside the control point, members of the military effects test group supervise the detonation.
5, 4, 3, 2, 1, 0.
After the detonation, test structures are studied, and the many scientific and military personnel involved return to their home bases to evaluate the results of the operation. After the 7 shots of Buster Jangle are complete, the test area lies dormant, waiting, ever ready for a future test. Our proving grounds, Enowetok and Nevada, stand ready to aid the scientists and the military in their job of preparedness, of developing weapons and doctrines for any possible future atomic war.
In the year 1826, Sir Humphrey Davy, as President of the Royal Society, presented Mr. John Dalton with a Royal Medal for his development of the theory of definite proportions, usually called the atomic theory of chemistry. This presentation set an official seal upon the emergence as a scientific theory of an idea of matter which had existed for over 2,000 years as a belief, unsupported by experimental proof. In Dalton's time, chemistry was becoming an exact science, thanks to accurate methods of weighing and analysis introduced in the 18th century. Dalton was able to work out fairly accurately the relative combining weights of many elements. In his new system of chemical philosophy, published in 1808, Dalton pointed out that these combining weights, which are constant for each particular compound, must be related to the weights of the ultimate particles or atoms of the combining elements. Thus, the atomic theory was reborn. According to Dalton, matter is composed of small particles which cannot be split up any smaller. These particles he called atoms. Our diagrams illustrate his ideas, but not, of course, the real shapes of atoms. He believes, secondly, that all atoms of one element are exactly alike, and differ from the atoms of other elements, and have a characteristic relative weight. Thirdly, he believes that atoms are indestructible, and cannot be created. Fourthly, that chemical combination occurs between small whole numbers of atoms. Such combinations of atoms are now called molecules. In any given compound, all molecules are alike. Dalton invented a system of symbols to represent the atoms of the different elements. He used these to show how the atoms combine to form molecules. Though some of his conclusions proved wrong, atomic theory was the foundation upon which the chemistry of the 19th century was built. Painstaking chemical analysis based on Dalton's theory and research arising out of Avogadro's hypothesis concerning molecules and gases enabled accurate atomic weights to be assigned to the elements. A connection was sought between atomic weights and chemical properties, and in 1869 this was supplied by Mendeleev's periodic table, which arranged all the elements then known in families according to their atomic weights and properties. Thus, the column headed by carbon contains a group of elements with mostly similar properties. The next column contains another group of similar elements, and so on. Now, from left to right, the elements are arranged in ascending order of atomic weight. The whole table fits together like a puzzle. The properties and place in the table of unknown elements were predicted, and the discoveries of later years proved the accuracy of these forecasts. The decomposition of solutions by an electric current was used as a means of chemical analysis in the early 19th century. By careful measurement, Michael Faraday was able to show that in such cases, a definite quantity of electricity was associated with definite amounts of the elements produced at the electrodes, that is, with definite numbers of atoms. Hence, he suspected that electricity itself might be atomic by nature. It was established that there were two kinds of electricity. Unlike charges attracted each other. Like charges repelled each other. By convention, these two kinds of electric charge became known as positive and negative. In a solution like common salt in water, the sodium chloride exists as ions or charged atoms of sodium and chlorine. When the solution is electrolyzed, the positive sodium ions travel towards the cathode and the negative chlorine ions to the anode. The work of many scientists on liquids and gases led to the theory that in all matter, molecules are in a state of perpetual motion. The botanist Robert Brown was the first to see in his microscope what is now called Brownian motion. This is the intricate motion imparted to fine particles in suspension in a liquid by the impact of molecules. One can imagine the tiny particles being pushed about by these ceaselessly active molecules. Each molecule is so small that 27 million are contained in 1 cc of gas at 0 degrees centigrade and normal pressure. The thinnest soap bubble that can be made by ordinary means is Each of these molecules would be 3 or 4 times the size of a small atom. This much was known at the close of the 19th century, which Lord Rutherford sums up in these words.
At the close of the 19th century, the labours of the chemists had resolved the matter of our material world into 80 or more distinct elements, and the atoms of these elements appear to be permanently indestructible by the forces then paramount.
The physicists of the 19th century were not less active than the chemists. Faraday investigated the conduction of electricity by liquids. Later scientists investigated the passage of electric currents through gases at low pressures with this kind of apparatus. Air is pumped from the tube until a luminous discharge passes from cathode to anode. As evacuation proceeds, brilliant rays are seen streaming from the cathode. The rays become invisible as pressure is reduced, but they still cause a faint green glow on the walls of the tube. This bell-shaped vessel shows the behavior of the cathode rays more clearly. At first, the current passes from the cathode to the edge of a fluorescent screen beneath it. Next, the glow of the cathode rays is clearly seen around the cathode itself. As the pressure continues to fall, the rays will disappear, but their presence is revealed by a powerful green glow where they strike the fluorescent screen. These cathode rays can be made to cast a shadow of an object in their path. This proves that they travel in straight lines from the cathode. The rays are capable of transmitting energy. The little vanes in this tube are turned by energy supplied from the motion of the tiny particles rushing up from the glowing cathode beneath. It can be proved that the rays are negatively charged. A wire connected to a plate on which the rays fall will discharge a positively charged electroscope. In 1897, Sir J.J. Thomson devised an apparatus to measure the ratio of charge to mass of these particles, which had been named electrons. He was able to make an estimate of the actual mass of the electron. In this apparatus, a luminous spot showed where the electron beam from the cathode fell on a fluorescent coating on the end of the tube. This beam could be deflected in one direction by an electrostatic field between charged plates, and in the other direction by a magnetic field. These fields could be adjusted to balance each other, and from their strength, the velocity of the particles could be calculated. Then, from the strength of the magnetic field alone, and the deflection caused by it, the ratio of charge to mass could be found. From experiments such as these, the mass of the electron has been estimated at 1/1840th of the mass of the hydrogen atom. Sir J.J. Thomson's own description of this tiny object has been preserved for us.
Could anything at first sight be more impractical than a body which can only exist in metals from which all but a minute fraction of the air has been extracted, which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a cloud of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known science.
Thus the existence of a negatively charged subatomic particle, the electron, was established beyond all doubt. It was even found possible to photograph the track of an electron. This was done by an ingenious apparatus invented by Professor C.T.R. Wilson. During the war, most people saw the vapor trails left by high-flying aircraft. Wilson, while investigating the ionization of gases by charged particles, built a chamber in which such particles could be made to leave a vapor trail. It consisted of a glass-topped chamber filled with moist air. The bottom of the chamber is really a piston head, supported by the air beneath. Connected by a valve to the main apparatus is a large vacuum chamber. When the valve is opened, the air beneath the piston is sucked into the vacuum, and the piston drops sharply, creating an expansion of the moist air so that a cloud is formed. Now, a charged particle from a source of radiation entering the chamber will ionize the gas along its path. Because of the sudden expansion, drops of moisture will condense on the charged atoms or ions along the path of the radiation and leave a visible trail. This is photographed by a synchronized electric flash. This apparatus, much improved since the original model, has proved invaluable in atomic research. Today, the electron is a commonplace. Any metal raised to red heat gives off electrons. The stream of electrons from this hot filament can discharge an electroscope. This is made use of in the radio valve, where the electrons from the hot filament can be used to send and detect signals broadcast over long distances. On this radar screen, electrons act as the eyes of a ship as it makes its way down the crowded river to the sea. And on the television screen, electrons paint pictures for our amusement.
The electron owes its practical utility to its small. It writes authority Shakespeare, say my use is great because I am so small.
The discovery of electrons raised big problems. Ordinary matter is neutral. For instance, it has no effect on an electroscope. Yet the cathode in this discharge tube can give off negative particles much smaller than atoms, which can turn the disk beneath. Some source of electrical equilibrium has been upset by this emission of negative electrons from neutral matter. Surely positively charged particles must have been left behind. Investigation of the so-called canal rays, first discovered by Goldstein in 1886, proved that this conjecture was true. If a series of small slits be pierced in the cathode of a gas-filled tube, a luminous ray can be seen streaming in the opposite direction to the cathode rays. These rays were subsequently found to be positively charged. Sir J.J. Thomson used this discovery to build an apparatus in which the mass of the rays could be measured. A fine beam of positive rays was directed onto a photographic plate. A magnetic field produced a deflection of the beam horizontally. Similarly, an electrostatic field produced a vertical deflection. In both cases, the different velocities of individual particles produced a line instead of a spot. If both fields were applied simultaneously, the particles fell on the plate in a parabola. The position of this parabola in relation to that of the undeflected spot was determined solely by the ratio of mass to charge. Hoffman was able to calculate the mass of these particles. He found that each particular type of positive ray consisted of charged atoms of the gas present in the discharge tube. Under certain conditions, the different types of glow due to positive and cathode rays can both be seen. These phenomena could only be explained by supposing that the neutral atom contained both positive and negative charges in equilibrium. The stream of electrons from the cathode detaches other electrons from the atoms of the gas through which they pass. These atoms immediately become positively charged and rush towards the cathode. If the cathode is pierced, they emerge as positive rays. The sequence of events resembles electrolysis, and these charged atoms of gas are called ions. A gas in which such conditions arise is said to be ionized. In 1896, Röntgen found that the green glow excited by cathode rays striking the glass was itself giving off rays which cause the fluorescent screen to become luminous. The rays could penetrate light metals, but not dense material like lead. The centerpiece of metal here is lead. The outer ones are aluminium. Lead stops the rays completely, but the lighter elements are penetrated and cast a light shadow. These powerful rays became known as X-rays, and doctors soon found that they could use shadowgraphs made with X-rays to see inside the human body. Dentists were able to study the internal structure of teeth. And industrial X-ray machines such as this one have been developed to search for hidden defects. But in 1896,
Radioactivity was the sign and measure of the instability of atoms, and that the atoms of uranium and thorium were undergoing a series of spontaneous transmutations.
Uranium, for instance, during its transformation to lead, gives rise to a whole new series of unstable systems, which ultimately break down to lead. The rate of change from one element to another may vary from a fraction of a second to millions of years. Only a few elements are normally radioactive. The majority are completely stable.
The next problem was to examine whether means could be found to break up the stable elements by artificial methods. Before this could be attempted, with any chance of success, it was necessary to have a clearer conception of the structure of atoms. The idea of the nuclear structure of atoms, which I suggested in 1911, has proved very useful for this purpose.
Experimental evidence supported Ballistic's idea. Alpha particles from a radioactive source, if limited by a single slit, will throw its image sharply across the direction of wind. A sheet of gold foil placed at the top of the blade causes a blurred image of the slit owing to the scattering of alpha particles by the heavy atoms of gold. Geiger and Martin investigated the nature and extent of the scattering. cloud chamber profile show. The existence of the atomic nucleus having been proved, the next thing was to find out the magnitude of the charge on it. See how this was done? Turn again to X-rays. We have already seen how X-rays are caused when electrons fall upon any substance. X-ray tubes were built, targets on which the electric beams fell, causing X-rays to give off at convenient angles. About 1912, it was found that X-rays could be refracted by a prism, thus light is refracted by a prism radius. H.G. Moseley used this discovery to build an apparatus to obtain X-ray spectra of different elements. The electron beam was directed downwards from the cathode onto the target and carried on the Uranium. X-rays give off to the target. A crystal enclosed in a vacuum chamber was so arranged that the X-rays passed through the edge of the constructed phase of the crystal. From the crystal phase, an X-ray spectrum was thrown onto the surface of the plate. Mostly found that each element used as a target gave off radiation, which included an X-ray of a characteristic wavelength. The X-ray spectra show this characteristic wavelength fits smoothly throughout the periodic system, according to a simple law. The wavelength could be specified by a number, Q, which increased by 1 each time he passed from one element to the next. The elements had already been arranged in the table according to their increasing chemical mass. Moseley related his Q numbers to these atomic numbers. He deduced that there was in the atom a fundamental quantity which increased by regular steps with one element to the next, and that this quantity could only be the charge on the positive nucleus. Thus, the number of each element in the table, the atomic number, acquired a Q significance. It indicated the positive charge on the nucleus of an atom, equal, though opposite in sign, to the number of orbital electrons in the particular atom. Of all atoms, hydrogen has the simplest structure, a nucleus and one electron. This nucleus, with its single positive charge, was written by Lord Ballistic as Protons. At this time, Rutherford was investigating the possibility of actually transforming the atom.
It became clear that to effect a veritable transformation of an atom, it was necessary to change charge or mass of the nucleus or both together. Now, the minute nuclei of atoms are held together by powerful forces, and to effect their disintegration, it seems likely that a very concentrated source of energy must be applied to the individual atom. The bombardment of the nuclei by the energetic alpha particles of radium appeared to be the most promising method for such a purpose.
In 1919, Rutherford found that nitrogen nuclei could be transformed by bombarding them with swift alpha particles, and that protons were ejected at high speed as a result. In effect, he added together helium and nitrogen, and changed them into oxygen and hydrogen. This was transmutation, the dream of the alpha, which the nuclear theory had at last discovered. Most significant of all, there could be no doubt that the proton, the hydrogen nucleus, was a fundamental particle in all atoms, the positive counterpart of the negative electron. How was the atom built up of these atomic bricks? Let us go back to our table of the elements. The atomic numbers represent the charge on the nucleus, and also number the elements according to their increasing atomic weight. Now consider these atomic weights. 1 for hydrogen, 4 for helium, 7 for lithium, and so on. Our figures are approximations to the nearest whole number, but they show that in most cases, the atomic weights are at least twice as great as the atomic number. How could this difference between mass and charge be accounted for? Consider the atom of one element, say lithium. It has 3 electrons circling around the nucleus. This nucleus, we know, must have a positive charge of 3. So we put 3 protons in the nucleus. Each has a charge of 1 and a mass of 1. But the atomic weight of lithium is 7 approximately. So the nucleus must have 4 more protons added to it to give a mass of 7. Now we have upset the balance of the charge. 7 protons, 7 positive charges. 3 electrons, 3 negative charges. There is only one way to correct this. 4 electrons must be added. Now our charge is balanced. The negative charge of 3 electrons is balanced by the outstanding positive charge of 3 on the nucleus. Such was the theory. But even in 1920, Rutherford suggested that there might be a neutral particle with the same mass as protons, which could account for the extra mass without affecting the charge. Ultimately, this proved to be another instance of his amazing insight. But in the years between, the drive to penetrate the secret of the nucleus continued unabated. From 1920 onwards, many other scientists used the discovery by radioactive source at the bottom of the case is emitting alpha particles. It is established between the wire and the outer case. The ionization caused by the alpha particles is collected, constituting a current to the central wire. Each alpha particle emitted ionizes the gas along its path into positive and negative ions, actually about 100,000 pairs of ions. These are pulled apart towards the electrode in the same way as the ions in the solution being electrolyzed. The tiny charge collecting on the central wire as a result of continuous alpha particle emission can be measured. Development of radio valves enabled the pulsive current from each single alpha particle entering the chamber through a micro window to be amplified until it could operate a kind of counter. Then Geiger and Miller developed an ionization chamber which could multiply the original effect by a principle known as gas amplification. Here is a modern Geiger counter, capable of counting at the rate of thousands per minute. Linked to it is an electric counter capable of high-speed recording. As the tiny speck of radium fitted to this rod is brought near the tube, the dials record the gamma rays from the disintegration of single atomic nuclei. These gamma rays are actually penetrating the walls of the tube, but charged particles can be counted by using a suitable type of tube. The ionization effect can be amplified and passed through a loudspeaker, so that each click represents the passage of a single particle, or as in this case, the ionization caused by a single gamma ray. The same voltage will operate an oscilloscope in which cathode rays trace on screen the effect of these nuclear explosions. Such sensitive apparatus, atomic disintegration is studied and accurate measurements obtained. About 1920, Aston, working at the Cambridge Laboratory, designed this ingenious instrument known as the mass spectrograph. Positive particles, or ions, produced in the same way as in Professor Thompson's apparatus, were allowed to pass through an electric field, which deflected the particles at varying angles according to their velocity. All particles of the same mass could be brought to a common focus on a photographic plate by means of a magnetic field of the right shape and intensity. In effect, Aston could weigh atomic nuclei very accurately. Work done with this apparatus showed that most of the elements accepted as indivisible by the chemists were actually mixtures of two or more substances of different atomic weights. The atomic weights of the elements have been very accurately determined by many chemists. Very few of them could be expressed as distinct cell numbers. Aston shows that chlorine, with its atomic weight of 35.5, is in reality a mixture in a definite proportion of two forms of the same element, one with an atomic weight of 35 and one with an atomic weight of 37. Such different forms of the same elements were called isotopes, and subsequent research has shown the number of elements of which isotopes exist is very large indeed. Little by little, hundreds of experiments all over the world built up the store of knowledge about atomic nuclei. As time went by, experimental evidence and theory both emphasized the increasing possibility that there did exist in the nucleus an uncharged particle of about the same mass as a proton. In 1930, Botha and Becker in Germany announced that they had noted what seemed to be an unusually penetrating gamma radiation produced by allowing alpha particles from polonium to bombard beryllium. The radioactive polonium gave off alpha particles which struck the beryllium. Radiation of some kind from the excited beryllium gave a high reading in the detector. Frederick and Madame Joliot-Curie measured the penetrative power of the radiation by inserting screens of varying substance. If these screens were of suitable density and thickness, most of them reduced the amount of radiation reaching the detector. But when screens containing hydrogen in the form of paraffin wax were used, a heavy increase in radiation was observed. In England, Sir James Chadwick confirmed the findings of the Joliot-Curie that this radiation consisted of protons. He suggested that the protons were ejected from the paraffin by an uncharged particle of about the same mass as the proton. Imagine that this billiard ball is a proton. No stream of light particles like electrons, no known type of wave, could have any more effect on such a body than these white grains have on the billiard ball. But another particle of equal mass would share its energy on the stream, just as this second ball imparts half its energy to the first as it pushes it away. A particle of unit mass, but without electric charge, and so very difficult to detect. Chadwick's reasoning recalled Lord Rutherford's suggestion of 1920, and the idea of a nucleus composed of protons and the uncharged particles, which were christened neutrons, was accepted. The field of force around the nucleus acts as a barrier against the penetrative power of charged particles. Neutrons, however, being uncharged, can majority of nuclei are much heavier than neutrons. If collision occurs, the neutron simply glances off and continues with a slight loss of speed. Now, paraffin is made up of carbon and hydrogen. Protons, or hydrogen nuclei, are no heavier than neutrons. So in collision, the neutron is able to transmit a large amount of energy to the proton. This is the explanation of the proton radiation observed by the Curie and Sir James Chadwick. The neutron once explained the existence of isotopes. Chlorine, for instance, has an atomic number of 17. That is, there are 17 electrons circling round the nucleus in which there are 17 protons. But chlorine has two isotopes. The atomic weight of one is 35, and of the other 37. If we add 18 neutrons to 17 protons, we get an atomic weight of 35. And in the 37 isotope, we have to add 20 neutrons to get the correct atomic weight. An isotope of hydrogen, called heavy hydrogen, has a nucleus consisting of the single proton of ordinary hydrogen plus one neutron. This nucleus, called a deuteron, has proved useful as a particle for bombarding atoms.
It became clear that to extend our knowledge, a more copious supply of bombarding particles of different kinds was necessary. Charged atoms of various sorts can be produced in vast quantities by the electrically charged reactor, and then accelerated by the use of high voltage. In this way, we have been able to obtain for our experiments in transmutation intense beams of proton and alpha particles, while the discovery of heavy hydrogen has given us a new projectile of remarkable efficiency in transmuting atoms.
Here at the Cavendish Laboratory in Cambridge, the experts of this modern alchemy of transmutation go about their business. The purpose of these huge electrical machines is simply to use electrostatic forces to accelerate beams of charged particles to very high energies, and with these atomic bullets, to bombard the atoms of various elements in order to see what changes occur in their structure. This laboratory grew out of the converted lecture room where, in 1932, Cockcroft and Walton operated one of the first successful machines to produce high-speed particles and obtained significant results by bombarding lithium. The machine you see is a descendant of their original set. Ions are produced inside the large mushroom-shaped insulator and are accelerated down the rearmost tower. The bombarding tube continues down into the room beneath, where the stream of charged particles can be bent by a powerful magnetic field and directed toward the target. In the Science Museum at South Kensington is preserved the observation cabinet and accelerating tube of the original voltage quadrupler used by Cockcroft and Walton. Three cylindrical metal electrodes are arranged vertically inside a glass tube where a high vacuum exists. Protons emerged from a narrow positive ray canal at the top of the tube. As the protons descended, they passed through intense electrical fields by which they were accelerated and sharply focused. At the bottom of the tube, they struck the element set up as the target for bombardment. Any particle ejected from the target element passed through a mica window and caused scintillation on a fluorescent screen, which could be observed through a microscope. With lithium as the target, a startling result was obtained. Alpha particles of high energy were ejected. This result received wide publicity. Through the press, the public imagination was stirred by the vague implications of the phrase, splitting the atom. But to understand the significance of this result, it is necessary to appreciate one of the most important aspects of Einstein's theory of relativity. Let us hear Professor Einstein himself.
It follows from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is just equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kocher and Walton in 1932 experiments.
In quiet, non-committal terms, the scientists summed up their results thus. It seems not unlikely that the lithium isotope of mass 7 occasionally captures a proton, and the resulting nucleus of mass 8 breaks into two alpha particles, each of mass 4, and each with an energy of about 8 million electron volts. This reaction, which you see here, can be written down. We start with lithium of mass 7, placing 7 at the top left corner of the lithium symbol. Its nuclear charge is 3, so we add the figure 3 at the bottom left corner. The lithium is bombarded by protons. That is, hydrogen is added rather forcibly to the lithium, so we put down plus H. Hydrogen has a mass of 1 and a charge of 1. As a result of the reaction, we get two alpha particles or helium atoms, each with a mass of 4 and a charge of 2. Note that the two sets of numbers add up to the same on each side of the reaction. 7 plus 1 equals 4 plus 4. 3 plus 1 equals 2 plus 2. The actual masses concerned in the reaction are known from mass spectra. On the left, they total 8.0241 mass units. On the right, 8.0056 mass units. There is a difference of 0.0185 mass units. Measured in grams, this amounts to 3.07 times 10 to the minus 26. It is this amount of mass which has been converted into the energy released in the reaction. In other words, the relationship between mass and energy is a constant and is expressed in Einstein's equation, E equals mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light. So, to find the energy released, we substitute for m the amount 3.07 times 10 to the minus 26. And for c squared, we substitute 3 times 10 to the 10th all squared, which is the square of the speed of light in centimeters per second. Thus, the energy released, expressed in ergs, is the product of these values, namely 27.6 times 10 to the minus 6. Now, the energy of each alpha particle released in the reaction can be directly calculated. It is 8.5 million electron volts. Or, more conveniently, 8.5 MeV. Thus, in our equation, we get E equals the sum of these energies, that is, 17 million electron volts. Measured in ergs, this becomes 27.2 times 10 to the minus 6. Thus, one calculation gives 27.2 times 10 to the minus 6, and the other 27.6 times 10 to the minus 6. A sufficiently close approximation to show that Cockcroft and Walton were correct, and that great energy can be released by splitting the atom. Man had set his foot firmly on the road towards the unlocking of great knowledge and power. All over the world, atomic physicists sought machines of higher and higher voltage with which to reach a goal that was still hidden. This machine is known as a synchrotron. In it, electrons are whirled around at fantastic speeds by new methods of using small high-frequency currents combined with powerful magnetic fields. High-speed electrons cause gamma radiation, which is betrayed by this sensitive detector. Even a thick screen is easily penetrated by this radiation. Energies as high as 8 million electron volts can be obtained on this machine, and in the United States, electrons of 100 million electron volts have already been produced. Giant synchrotrons are now being built to accelerate positive ions. Hidden behind thick concrete barriers to absorb the dangerous gamma radiation is this latest type of linear electron accelerator, in which electrons pass through a series of alternating magnetic fields arranged in line along a corrugated tube, known as a waveguide. Eventually, this machine will hurl electrons at its target with an energy of 5 million electron volts. Older in conception, but impressive in size and shape, is this electrostatic generator, designed to accelerate positive particles such as protons and neutrons. And this is one of the newest Van de Graaff machines to be built in England. These are so called after the American scientists who first designed them. Electric charge is sprayed onto a moving belt inside this tower and carried to the top of the accelerating tube, where the high potential thus generated is used to drive the particles down towards the target at great speed. When in operation, the machine is enclosed in a high-pressure casing, which permits the potential of 2 million volts to be built up. Most impressive of all in their suggestion of a well-done world are these million and 2 million volt generators in the Cavendish laboratory at Cambridge. This is a cyclotron, one of the most famous of these accelerators. The inventor was Professor E.O. Lawrence of the University of California. The accelerating chamber, or tank, is fixed in the middle of the apparatus, between the poles of a very powerful electromagnet. The principle is ingenious. The tank, which is completely evacuated, contains two hollow D-shaped electrodes, to which a high-frequency alternating current is fed. Minute quantities of the gas which is to provide the ions are admitted. The ions are produced in the center of the tank by electrons from the small arc or filament. Once produced, they are sucked into one or other of the Ds by the powerful electric field. But this movement of the ions takes place between the poles of a big magnet. Consequently, the ions will travel with a circular motion in the magnetic field. The alternating voltage accelerates the particles each time they cross the gap from one D to the other, so that they are whirled round faster and faster until finally they are led off towards the target by means of a charged deflector plate. Here, an element is being set up and bolted into the target chamber, ready for bombardment. Nowadays it is known that almost all elements, if bombarded by neutrons, can be made radioactive for varying periods. Irene and Frederick Joliot-Curie first produced artificial radioactivity, and Professor Fermi made brilliant advances in this field. As the operator moves off towards the control panel, he passes through the water screen, 3.5 feet thick, which protects the scientists from the intense radiation produced by beams of accelerated particles. switch on the complicated high-frequency installation which feeds current to the Ds. To build and operate such machines, atomic physicists become engineers, overcoming step-by-step problems of high vacuum, screening from harmful radiation, construction of special magnets, and so on. For the production of neutrons, neutron beams are usually found the most convenient. When the neutron strikes the target, it splits out, liberating a neutron, which easily penetrates to the nucleus. At last, the full power begins to flow. Through the observation window can be seen the arc in the center of the tank, and round it the pulsation of the accelerating particle. Some idea of the neutron's effect on a nucleus can be given by this simple experiment. Imagine that the saucer is the nucleus of an atom. One might think that the neutron would go straight in and out on the other side, like this. Now let us fill the saucer with marbles to represent the particles in the nucleus. If we let the neutron marble roll down into the nucleus, it will jostle the others but remain in the saucer. The nucleus has captured a neutron. It becomes unstable and gives off its excess energy as beta and gamma radiation. If the neutron marble enters the saucer with a somewhat greater energy, one or more marbles will be knocked out. Thus, neutron capture can eject particles from the nucleus and cause disintegration. Outside the laboratories, the world was disturbed by the strident voices of evil men and the ever louder rumble of approaching war. But in 1939, atomic scientists made a fateful discovery. Professor Frisch, now at work in England, was closely concerned in them.
Early in 1939, Professor Hahn and Dr. Strassmann in Germany found that uranium, bombarded by neutrons, gave rise to what appeared to be an isotope of barium, only about half the atomic weight of uranium. Professor Lisa Metzler, who had previously worked with Hahn and Strassmann, was by then in Sweden. He told me of their puzzling discovery, and together we considered the possibility that the uranium nucleus sometimes broke into two halves. We found that such a process, although quite unexpected, was indeed compatible with what we knew about atomic nuclei. If we were right, a great amount of energy had to be released in such a process, and I was able to show this experimentally.
Hahn and Strassmann's evidence for the disintegration of the unstable uranium gave rise to elements such as barium in the middle of the atomic table, was purely chemical and required a physical confirmation before it could be accepted. The uranium nucleus is unstable and radioactive, as is known from its ability to emit an alpha particle. If a uranium nucleus could indeed capture a neutron, becoming more excited and splitting into two approximately equal fragments, it was to be expected that a large amount of energy would be released in such a process, the fission fragments being hurled apart with great velocity. Professor Frisch obtained confirmation that this was so in an experiment essentially similar to the one shown here. Uranium was placed in the ionization chamber, which was placed over the end of a bombardment tube through which high-energy neutrons could be sent. The chamber was connected, as you see, to an oscilloscope. The trace you see here is made by alpha particles from the radioactive uranium. Now the high-tension set is switched on, and the uranium is bombarded by neutrons. On the screen of the oscilloscope, the fission pulses reveal the large amounts of energy released when uranium atoms are split. If each fission had to be provoked by elaborate apparatus like this for accelerating particles, there was no hope of deriving useful energy from the process. But each fission was found to be accompanied by the release of a few itself capable of provoking more than one fission, and so on. There is thus the possibility of a self-sustaining chain reaction. The reaction can begin without any neutrons being supplied from outside, since a few fissions are always taking place spontaneously. These would supply the fused neutrons. While these facts were being investigated, the political high tension in Europe sparked over into actual war. Years of aggression had at last forced the Western democracies to challenge the attempt at fascist domination of the world. Under wartime security, research on the use of atomic energy was pushed ahead. What was the problem to be attacked? The possibility of a fast chain reaction suggested an atomic bomb. There are two isotopes which make up the bulk of natural uranium. The atomic weight of one is 238, of the other 235. Over 99% of natural uranium is U-238. U-238 undergoes fission only with very fast neutrons. Many neutrons are scattered by uranium atoms and lose the speed necessary to cause fission. So, a divergent chain reaction will not take place in uranium, which is predominantly U-238. U-235, on the other hand, undergoes fission with neutrons of any velocity. It seemed possible that a controllable chain reaction might be achieved by using slow neutrons to cause fission in U-235. Using pure uranium containing both isotopes, a pile was built, in which uranium rods were embedded in a mass of pure carbon in the form of graphite. Neutrons produced in the uranium were slowed down by collisions with the light atoms of the carbon, the moderator as it is called, giving them a chance to cause fission in U-235. A slow, controlled chain reaction was achieved on December the 2nd, 1942. If natural uranium and a moderator were replaced by a small amount of pure U-235, slow neutron reactions would give place to fast neutron reactions. Fissions would occur, but so many neutrons would escape before hitting another nucleus that no chain reaction would build up. But if the amount of U-235 became larger than a certain critical size, a fast chain reaction would take place in less than a millionth of a second. This would produce a violent explosion. A simple mechanism for an atomic bomb thus suggests itself. Take two pieces of U-235, each smaller than the critical size, but which, if placed together, exceed that size. They are driven together, and so U-235 became bomb material number one, and its separation from U-238 became a war priority. The behavior of U-238 in a pile is also of great importance. Slow neutrons are sometimes captured by U-238. No fission is caused, but this nucleus becomes U-239. This is unstable. A beta particle is emitted, causing a change to a new element with different chemical properties, Neptunium-239. This new element is also unstable. Another beta particle is given off, forming another completely new element, Plutonium-239. Now, Plutonium-239 has fission properties similar to U-235, and will be built up by this process of neutron capture and subsequent beta disintegration throughout the uranium in the pile. Being a different element, it can be separated by chemical means from the uranium and used also for a bomb. So, plutonium is bomb material number 2. Huge plants for the production of pure U-235 and of plutonium arose in the United States. By 1943, it had become plain that Great Britain was fully extended in war production. In consequence, her nuclear physicists crossed the Atlantic to continue with American and Canadian colleagues the brilliant work already done. The main practical effort and most of its prodigious cost now fell on the United States, where very active research has been going on since 1939. The processes were laborious, and at all times elaborate precautions had to be taken by workers on the atomic pile and in the chemical laboratories because of the ever-present dangers from gamma and neutron radiation. Danger signs and warning signals, lead and concrete shields, remote controls, detectors, protective clothing. These were the everyday equipment of the men who worked to make the material for the bomb. At last, in the desert of New Mexico, the first atomic bomb was set off under conditions of great secrecy. Thousands of calculations, years of work, reached their climax in this moment of dreadful splendor. Within a few weeks, the bomb burst upon Japan, and the news of it upon a startled world, which has now seen this supreme destroyer in action 5 times in all. We are aware now of the compelling urgency of the situation created by the bomb. We know that war must be banished, or else our civilization may die, as Hiroshima died on that summer morning in 1945. The tale has been told in full by those who lived through it. A city destroyed in an instant, 60,000 people dead, many from flash burns, thousands more by blood, many from strange sicknesses caused by gamma radiation. For a short while, the world was content to accept the fact that atomic energy, by destruction, had brought peace. Then came the question, can this power be controlled to serve mankind? Professor Einstein has recorded his opinion.
To give any estimate of when atomic energy can be applied to construct this surface is impossible. What now is known is only how to use a fairly large quantity of uranium. The use of quantities sufficiently small to operate, say, in a car or an airplane is as yet impossible. Presumably, all materials which may be used for such purposes will be among the heavier elements of high atomic weight. Those elements are relatively scarce because of their lesser stability. So, though the release of atomic energy can be, and no doubt will be, a great boon to mankind, that may not be for some time.
The core of the problem is to turn the atomic pile into a heat engine. The release of energy in a pile results in the generation of heat. If the reaction is allowed to run fairly fast, a cooling system is necessary to absorb the heat. To control the rate of reaction, rods of cadmium or some such substance must be introduced, which can absorb neutrons if lowered into the pile. Now, if the cooling fluid, probably helium gas, were passed through a heat exchanger containing water tubes, the water could be heated up and turned into steam. Most of this part of the installation would have to be screened off by heavy concrete or water shields and operated by remote control. The steam could be used to drive turbo generators to provide electricity in a powerhouse or in a big ship. This adaptation of the atomic pile as a source of heat energy is now being tackled in the United States and Great Britain. The use of radioactive byproducts from the pile is also being investigated. Medical research is now employing new tracer techniques based on radioactive elements. In this test, a radioactive sodium source is being used to check blood circulation time. The Geiger counter picks up the radioactivity from the sodium. Now the doctor prepares to inject the sodium into a vein in the patient's foot. The radioactivity will be picked up by the counter as the sodium in the blood reaches the patient's groin. The injection is made, and the scientist starts his stopwatch. The radiosodium travels up the leg in the bloodstream. The counter is shielded from outside radiation by a lead block with a slot beneath. Now, 10 seconds have passed, and the counter reveals the arrival of the radiosodium. From such experiments, it is hoped to devise a test to help prevent some of the complications which follow childbirth. Other possible sources of atomic energy are suggested by what is known as the generation of solar and stellar energy. Under conditions of tremendous heat and pressure, complicated nuclear reactions are provoked, resulting in the building up of helium nuclei from hydrogen. In this process, large amounts of energy are released. Perhaps man may one day obtain energy by building up heavier atoms from the lighter ones. Meanwhile, the representatives of the United Nations in conference strive for some formula to banish the atomic bomb and to permit the blessings of atomic energy to be used for peaceful ends. Great Britain's research establishment at Howell is under the direction of Dr. Cockcroft.
You have seen the story of a remarkable scientific achievement based on the work of scientists of many nations, but owing most of all to the work of Rutherford and the School of Nuclear Physics which he developed. The final achievement of the release of nuclear energy for war was due largely to the scientists and engineers of the United States, stimulated and helped by British physics. We have now the task of using the immense power of nuclear energy for peaceful purposes, for the production of radioactive materials, for medical and biological research, and for the generation of heat and power. With our present knowledge, it is possible to design nuclear power stations which will produce power at a moderate efficiency. Until we acquire operating experience of these plants, we do not know how economical they will be, nor are we sure of overcoming all the technical difficulties which will occur in a large-scale development of nuclear power. Nevertheless, there is a real promise that over the next few decades, world power resources can be greatly increased, and that the very great benefits that will be obtained will do much to increase standards of living. It is the hope of every scientist that nuclear energy will lead to the establishment of a world organization for the effective control of all weapons of mass destruction, and through this to the abolition of war.
From Dalton's theory to atomic power. It is a long road, but the landmarks are clear. With the atomic theory as a basis, a pretty complete picture of the elements of our material world was fitted together during the 19th century. The discovery of electrons, the realization of the nature of positive rays, the strange powers of X-rays revolutionized conception of the nature of matter and of the atom itself. The study of radioactivity, first investigated by Becquerel and then by the Curies, led Lord Rutherford to make the greatest single advance in atomic theory. He pictured a small, heavy nucleus in the atom, round which the electrons revolved. In 1919, Rutherford discovered how to change one element to another by bombardment with alpha particles. He suggested that the nucleus of the atom might contain protons and uncharged particles of about the same mass. In 1932, scientists could say with certainty that the atom contained electrons carrying unit negative charges and a nucleus built up of protons carrying unit positive charges and of neutrons, uncharged particles equal in mass to protons, whose existence was proved by Sir James Chadwick. In 1932 also, Cockcroft and Walton split the lithium atom by bombardment with protons and found that mass could actually be translated into energy in perfect accord with Einstein's theory. Atomic disintegrations provoked by great machines became a commonplace of well-equipped physics laboratories. In 1939, uranium fission was first noted. The possibility of a self-sustaining chain reaction suggested the wholesale release of energy. Controlled chain reactions were achieved in the atomic pile. The imagination of the world has been stirred by the prospect of adapting such piles to use as sources of heat energy and as sources of radioactive materials for use in medicine. In research laboratories, the scientists are even now writing fresh pages in this unfinished story. But overall, the smoke of the atomic bomb hangs like a pall. If we are to reach the future that promises so bravely, the peoples of the world must see that this new power is wisely used.
This film is concerned with the effects of high-altitude nuclear explosions on radars, optical sensors, and communications. To understand how nuclear explosions affect such systems, it is first necessary to understand the interaction of explosions with the atmosphere. We will discuss this interaction, or phenomenology, for explosions at very high altitudes in the ionosphere and in the upper atmosphere. We shall not consider the blast and other lethal effects that nuclear explosions produce. The air we breathe consists almost exclusively of gases and are electrically neutral in their ordinary condition. The number of electrons shown here is of course symbolic rather than literal. As we progress towards the top of the atmosphere, however, the gases are exposed to powerful X-ray, gamma ray, and ultraviolet radiation from the sun and from cosmic rays. Above about 90 kilometers, radiation increasingly breaks more of the molecular gases into their atomic or single atom state. This dissociation, primarily from the ultraviolet radiation, affects as much as 50% of all molecules at altitudes of about 100 kilometers. The cosmic and particle radiation also causes ionization. Detachment of the single electron leaves the remainder of the atom or the molecule with a positive charge. This can happen to single atoms or to either one of the atoms of a molecular pair. Being electrically charged, free electrons are attracted to and tend to recombine with positive ions at the first opportunity, thus again creating electrically neutral units. If an electron does not recombine with a positive ion, it can be taken out of circulation by temporary attachment to a neutral atom or molecule, which then has a negative charge until the electron is snatched away by the stronger attraction of some positive ion. Because of the strong recombination tendency, ionized gases will not remain in that condition unless there is a constant supply of energy to cause new ionization as fast as the previous ions can recombine. The first significant quantities of naturally occurring free electrons begin to show up at an altitude of approximately 60 kilometers, which we therefore consider as the bottom of the ionosphere. From there on up to heights of several hundred kilometers, free electrons become more and more prevalent. Their rate of increase with altitude is non-uniform, and there are several clearly defined regions which exhibit distinctive electromagnetic characteristics. The first region is the D region, frequently called the D layer, between 60 and 90 kilometers above the Earth. Centered at roughly 120 kilometers is the E region. At 200 kilometers, the F1 region. And finally, at some 300 kilometers, the F2 region. In the relatively dense atmosphere of the D region, there are sufficient numbers of diatomic positive ions that no free electron can exist for long without either combining with one of these ions or becoming attached to a neutral particle. There is no solar radiation to produce a resupply of new ions in the Earth's shadowed or night regions. However, cosmic radiation provides a source of ionization both during the day and at night. Nevertheless, the absence of solar radiation at night allows recombination to proceed more rapidly than ionization,
and the free electron density is reduced compared to that during the day. Up in the F region, however, the extremely rarefied atmosphere allows a large free electron density to exist throughout the night. Shortly after sunrise of the following day, the D region ionization, consisting mostly of electrons, is re-established by solar radiation. We are concentrating attention on atmospheric ionization processes because the free electron density at the various altitudes determines the signal propagation behavior of many of our radar and long-range communication systems. Now, in what way do high-altitude nuclear explosions affect these free electron densities? To begin with, roughly 70% of the total energy produced in a nuclear explosion is emitted in less than a microsecond as a flash of X radiation. A few percent more of the bomb energy is emitted as prompt gamma and neutron radiation. Most of the remaining energy appears as directed motion or kinetic energy of the expanding explosion debris. Delayed gamma and beta radiation from this radioactive debris material emits some 5% of the total weapon energy over a longer period of time. We will examine the effects on the atmosphere of nuclear detonations at 50 kilometers, 100 kilometers, and 250 kilometers altitude. First, let us consider the events that follow the detonation of a sub-megaton weapon at a moderate altitude of 40 to 50 kilometers. Most of the X-ray energy is deposited near the burst point, heating air to incandescence. The prompt gamma and neutron radiations from the explosion can, on the average, travel large distances before colliding with air particles. Therefore, the ionization caused by such collisions is spread out laterally over a region several hundred kilometers in diameter. Radiation in an upward direction increases the D-layer ionization, which we symbolize with the blue shading. It is important to realize that the greatest range of these radiations will be upward and horizontal, because the exponential nature of our atmosphere causes its density and absorbing qualities to decrease very rapidly in upward directions. Specifically, each 15 kilometers change in altitude in either direction will make about a 10-to-1 change in air density. At 45 kilometers altitude, the density is approximately 1,000th of the air density at sea level. Coming back to our explosion, the X-rays heat the surrounding air to incandescence. Within a tenth of a second, the tremendous radiant energy output and gas expansion processes have created a fireball of superheated air several kilometers in diameter. Inside the fireball, both the air and the smaller central mass of expanding weapon debris are fully dissociated from the molecular into the atomic state, and the atoms themselves are highly ionized. In another view, a high-velocity shock wave is seen to race outward from the radiation front, which is still at a temperature on the order of 10,000 degrees. The fireball expands at a slower rate to a diameter of 10 kilometers within about 5 seconds, during which time it also begins rising upward at a rate approaching 300 meters per second due to the buoyancy of its heated low-density gases. We watch the remainder of the explosion development through a camera located directly underneath the fireball. Sometime during the first minute, the rising cloud of fireball and debris material from explosions at this or lower altitudes interacts with the surrounding air. The fireball transforms into a torus or donut shape. Both gammas and high-energy electrons or beta rays are continuously emitted from fission fragments in the debris. The cooling fireball and debris mixture, no longer luminous, continues to rise and expand, reaching a diameter of about 40 kilometers at 1 minute. It finally stabilizes some minutes later at an altitude of about 100 kilometers until dissipated by atmospheric winds. We will next consider a nuclear explosion of large yield at an altitude of 100 kilometers. where the atmosphere is less than 1,000, as dense as it was at 50 kilometers. The initial heavily ionized X-ray fireball will be an order of magnitude larger than from our low-altitude shot, and much more tenuous and less brilliant in appearance, because so much of the X radiation escapes to large distances, over which it causes a significant ionization increase without luminosity. The atmosphere is so rarefied that the highly penetrating prompt gamma and neutron radiation from the explosion will produce only negligible concentrations of new ions in horizontal and upward directions. Ions are produced in the D layer and at lower altitudes. The hot and rapidly expanding fireball rises ballistically with something over 5 times the average velocity seen for the lower shot. Its diameter is some 300 kilometers after the first minute. Magnetic forces progressively distort the rising material, elongated along the geomagnetic field lines. Maximum altitude on the order of 1,000 kilometers is reached in 7 or 8 minutes. With the upward ballistic impulse exhausted, the material being heavier than the ambient atmosphere tends to fall back to denser regions on the order of 150 to 200 kilometers. The fall is oriented primarily along the Earth's geomagnetic field lines. The diameter is several hundred kilometers with a thickness perhaps a tenth as great. The diffuse radioactive debris continues emitting both gamma and beta radiation with significant intensity for many hours after the explosion, thereby continuing to produce ionization. Most of the ionization from gamma radiation occurs at altitudes near 30 kilometers. However, ion lifetimes are very short down in such relatively dense air. Reattachment is so rapid that we actually find the greatest net population of gamma-produced free electrons up at the D layer altitudes, where the reattachment rate is much lower. The other major radiation from the debris, the super high-velocity electrons from fission fragment decay, referred to as betas, are less penetrating than the gamma rays. Most of the downward-directed betas dissipate their energies in the D region at 60 to 80 kilometers, adding to total ionization in that region primarily by collision with neutral particles. The area of the ionization region created by beta radiation will correspond roughly in size to the area of the stabilized debris material itself. Actually, being electrically charged, the beta particles are constrained to follow the Earth's geomagnetic field lines. Thus, a region of ionization commonly called the beta patch is caused by these downward traveling electrons. The few beta particles that start out parallel to the field line will continue to follow them. If the particles encounter the field lines at an angle, however, they will spiral around them. Here we see beta particles streaming along the magnetic field through the fireball and debris of a burst. Those electrons ejected upward may be trapped along the Earth's magnetic field lines and are mirrored back and forth if the reversal or mirror point is substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle, soon will be lost by collision with air molecules. This collision excitation mechanism is generally accepted as one of the causes of auroral displays. Thus, a nuclear burst at sufficiently high altitudes can produce auroras at conjugate points in both hemispheres. Since the debris from a nuclear detonation begins radiating at the moment of the explosion, its conjugate point auroral effects can be expected to change location as the debris rises and intersects with successively higher magnetic field lines. Note that when the debris is located below about 200 kilometers, most of the electrons shuttling along the field lines will be lost in the atmosphere on their first pass, with very little mirroring back to the other conjugate point. We will next consider a nuclear explosion at altitudes above 250 kilometers. Mass asymmetries in the construction of the nuclear device and its carrier can be very important and are observable in this 400-kilometer explosion. At this very high altitude, a substantial change occurs in the mechanism of containment, the forces which slow and finally stop fireball and debris expansion. While ordinary hydrodynamic pressure resists the explosion expansion at low altitudes, geomagnetic back pressure becomes increasingly important at altitudes above 100 kilometers. The heavily ionized debris and gases in an expanding fireball are electrically conductive, so the Earth's magnetic field tends to be excluded from that region, creating a so-called magnetic bubble that presses back against the expanding gases. At great altitudes where air pressure is negligible, expansion might continue indefinitely if it were not for a collisionless process in the debris and surrounding air plasmas, which permits a degree of coupling between the weapon debris and the ambient atmosphere. The degree and nature of the coupling are believed to be very dependent on yield and burst altitude, but these processes remain major unknowns in the phenomenology of very high altitude nuclear explosions. Looking back again at another weapon effect on the atmosphere, most of the prompt gamma radiation is deposited between 25 and 30 kilometers altitude. The air molecules are ionized. The free electrons split off and start spiraling around the magnetic field lines. Each spiraling electron emits minute radio waves. All of the electrons exist nearly simultaneously, and the minute radio waves add together. This is the primary source of the high-altitude electromagnetic pulse, or EMP, which is a broad band pulse of radio frequency energy radiated from the deposition region. When this electromagnetic pulse is coupled into a system, very large voltages and currents may be induced. Other EMP generating mechanisms are operative in other burst regimes, but are outside the scope of this film and will not be described. In brief summary of the important effects on the ionosphere, we see that a nuclear burst in the 40 to 50 kilometer region produces first a heavily ionized fireball area, while the flash of prompt gamma and neutron radiation causes significant ionization lasting for several minutes, extending to large distances horizontally and upward, but with only minor range and duration in downward directions. Debris radiation continues to create intense ionization in the region of the fireball while it rises. At all explosion altitudes substantially above 50 kilometers, the immediate radiation produces almost completely ionized fireball regions of multi-kilometer dimension. Its strong but radially decreasing ionization extends to many hundred kilometers. The fireball and debris materials rise to maximum heights of from 100 to 1,000 kilometers as the first height is raised from 50 kilometers to the 100-kilometer region. Unlike debris from the lower explosions, material from the higher explosions falls back from its maximum altitude, ultimately settling around 200 kilometers. With rising burst altitude, greater quantities of beta particles and charged debris particles will shuttle north and south along the magnetic field lines to conjugate points in both hemispheres. Both beta ray and debris interaction with the atmosphere at those points will, for a number of hours, create significant ionization with vivid auroral effects and radio disturbances. Debris gamma and beta radiation will also enhance ionization in the D region at both conjugate points. Other phenomena will associated with irregular structure in nuclear burst ionized regions are also important to communications, infrared, and radar systems. One is the eventual development of magnetic field-aligned filaments, or stria, in ionized regions. Irregular ionized structure also results from the upwelling or heave of explosion-heated air above 100 kilometers altitude. These phenomena are treated in greater detail in Part 2 of this film, which considers the effects of atmospheric ionization on military systems.
Ladies and gentlemen, you've heard the reports that enemy planes are approaching. In less than 3 hours, an H-bomb might fall over Portland. Like myself, I think you're going to be very interested in these stories we'll tell you. And in this age of missiles and man-made nukes, Exxon's attitude. There are no actors in this story. There are a lot of people. People of the city of Portland, Oregon. And what happens to them? Or should happen on the day that you This is the line between the mountains and the sea, between the snow-capped
1:47 Greenwich time. That is 1:47 p.m. Pacific Standard Time. And now I would like a brief situation report from all departments on how we stand. First, John, what is the fallout situation? Jack, according to our latest weather information, winds will continue in a northeasterly direction at about 10 knots. Let's face facts, gentlemen. If we have a blast on target, downtown Portland, it'll be hours and probably days before we can get back in. Engineering, Gordon Burke.
That report, 80% of city-owned public utility equipment has been successfully evacuated from the city. However, there is one group of electric company trucks out on the west side. We're working now on a plan to get them out.
Fire Department, Chief Simpson.
Fire department's initial dispersal plan is in effect. Several units have already moved out to their respective dispersal points. Engine 24 and Engine 30 are currently fighting the residential fire. They will stay on the job until this fire has been controlled.
Police, Chief Hilbert.
After police activities, the city is about 65% evacuated. Traffic appears to be moving at about 15 miles an hour outbound. State and county police set up effective roadblocks, diverting inbound traffic, thus enabling us to use all lanes for outbound traffic.
Emergency Medical, Dr. Metter.
City hospitals are continuing to evacuate. Emergency hospital units are functioning in Forest Grove, Mount Ames. Others should be heard from soon. You might be interested in knowing that en route, one boy and twins were born.
Dutch Lane, welfare.
As the reports continue, it is obvious that the Portland plan was working smoothly. Only 7 years earlier, Portland had no civil defense. It was then that the idea that civil defense was not to be separated from normal government evolved. And in 1952, a one-mil tax levy to finance the plan was put on the ballot by unanimous decision of the City Council. After civil defense leaders went out in the campaign, the people voted to tax themselves to protect themselves. And later, the city charter was amended to assure continuity of government, so that in an emergency like this, should the executive branch become a casualty, they would automatically be replaced by a legally established line of succession of other experienced city officials. The people, both now and after the emergency, are assured of continuity of their government.
Schools report complete evacuation. No panic among the children. They've rehearsed this before. Reports from industries indicate approximately 90% evacuation. I think we're doing quite well.
So, it's 1:25, some 22 minutes till 0 hour. Portland seems to be doing quite well. Should a bomb fall now, city officials and city services will be able to carry on. In the meantime, vital messages are passed on to maintain contact with state and county headquarters.
Okay.
state and local governments to carry out their responsibilities in the event of a massive nuclear test. Each new scientific development in weapons of war presents a new challenge. The people of Portland, through working together, they're ready. There really were a day called X. How about you?
Joint Task Force 8 under the command of Major General Alfred B. Stark
accomplished by placing an instrumented ship array in an open ocean area south of Hawaii to control and observe technical data from the detonation of the test device, which will be brought by a B-52 based in Hawaii. This air dock will have a twofold mission. It would provide for the proof test of weapons which, during the moratorium, had gone into the national stockpile without having been tested in weaponized form. And it would provide for the test of new development devices of advanced design. Supplementing the ship with that, specially modified aircraft diagnostic platform. While the open ocean preparations were underway, negotiations were being conducted with the British government for the use of jointly owned Christmas Island, 1,200 miles south, as a location for the aircraft. In mid-February, the task force was notified that the necessary agreement had been reached. Because of the many technical advantages expected from the use of the island test base, plans were immediately halted to move the weapon development testing there. This location split was indeed a substantial effort, to drive the first shot readiness date only 6 weeks away. The main features of the 1962 test program were by now essentially defined, although many details were far from constant. This fluid condition continued, as development throughout the test period brought forth new requirements. Although work in each of the 4 main areas was proceeding simultaneously, in this film, each of the locations will be considered separately, beginning with Christmas Island. Late in March, the Joint Task Force headquarters began to move to Christmas, the main forward location for the first phase of the operation. This 222 square mile atlas, hard by the equator, is governed by the British. They had used it for their nuclear test operations from 1956 to 1958, but equipment connected with their tests had been withdrawn and deserted. Equatorial weather had thickened. The task force's additional needs required extensive preparation for the task force program. Since the atoll possessed no harbor, all ship-transported equipment, materials, and continuing supplies had to be transferred to lighters and barges in the road, moved to the port of London for all. Inland, Christmas positions relative to the detonation. Positioned at various distances from Johnston Island were 9 test ships, including the downrange anti-missile measurements program ship American Mariner, on loan from the Atlantic Missile Brigade. Pod recovery and surveillance ships were also on station, along with an aircraft carrier. Marine helicopters evacuated from the island all personnel non-essential to the actual operation during each event. But Johnston Island itself was only the hub of an extensive network of land, ship, aircraft instrument stations radiating in all directions deep into both northern and southern hemispheres of the Pacific. Between the northern arc, Okinawa, Adak, Fairbanks, and Palo Alto, the Polynesian islands of Tonga Tapu and Rarotonga, far south of the equator, Johnston Island's southern magnetic contour area, a roll call of islands hosting eclectic instrument stations, evokes images both geographical and logistical, especially the latter, with over 200 ground instrument stations prepared, installed, and expanded. High-altitude effects were also secured from aircraft platforms. More than a dozen planes took to the air from Hickam Air Base in Hawaii for each event, and 3 more from Nandi Airport in the Fiji Islands. Besides the instrumentation ships at Johnston Island, 2 minesweepers put to sea from Pearl Harbor for electromagnetic station equipment, and from its mooring at Tango Tango in Samoa, the instrumented motor ship Acania moved out prior to each shot day beyond its mid-ocean station. Johnston's opening event on May the 2nd was a daylight certification shot, testing all systems during flight trajectory, but without nuclear work. This group test was as planned, achieving all program objectives. Hereafter, the course of shot test is not part of this script. The first 2 hot launches did not carry through to nuclear detonation. Neither of the failures caused missile or war. On 8 July, the 3rd nuclear launch, another prize of a very high-altitude starfish, was flawed, including the performance of many auxiliary instrumentation rockets sent into selected trajectories about the birthplace. Starfish detonated at planned strength and height, producing wide upper atmosphere glow and extensive auroral effects. Here is how it appeared from Mount Haleakala, Hawaii's island of mountains. Recovery of the instrumentation pods ejected from the Starfish missile involved pre-dawn ship, patrol plane, and helicopter convergence in the splash area, drawn by radio signals, flashing lights, and green dot. As soon as the pods were fished from the water, they were taken to the Johnston Island recovery area for removal of the scientific instrumentation. The second bluegill attempt was made on 25 July, but a one-of-a-kind missile misadventure caused by a sticking fuel ring destroyed the core and its warhead on the pad. The pad itself suffered extensive damage, including long-life radioactive contaminants. Repairs to permit another cry of bluegill caused a significant delay. Additional construction on Johnston Island during this incident, as well as the scheduling of more shots, reflected the value attached to the testing being carried out on Operation Dominic. 3 more high-altitude effects missile events were added to secure data at different heights. Also, 5 more over-ocean air drops were scheduled. These will take place within the Johnston Island range. Besides the second floor launch pad, construction included facilities for the launch of XM-33 rockets, Nike Hercules missiles. October, high-altitude testing was resumed, resulting in another failure of a blue blade. This time due to internal missile guidance malfunction. It was the last of Isotope. All remaining launches culminated in detonation at their planned altitude. First came checking, boosted to altitude by a Sergeant Engine XM-33 rocket. Besides furnishing new basic scientific data on upper atmospheric phenomena, the tests fulfilled vital military aims of providing information on the offensive and defensive aspects of nuclear attack upon incoming ballistic missiles, as well as data on blackout effects on radar and communications. Meanwhile, the 5 additional weapon development aircraft tests in the Johnson Island area were conducted. To gain the scientific information, the airborne array refined at Fission was utilized as the sole diagnostic force. The original C-130 aircraft joined by DC-135 jets carrying additional diagnostic gear. The makeup of the remainder of the test aircraft formation was generally the same as at Fission, including the post-shot B-57 diagnostic cloud section, this time staging through Johnston Island, to conserve flight hours and to reduce pilot radiological dosage accumulation after cloud section. The air array was under the guidance of the Air Task Group Commander, one of the RC-121 aircraft, while overall control was maintained by the Joint Task Force Commanders from flag plot in the fleet near the Dop area. Target rafts were again used as guidance for orienting the air array, the point of aim for the B-52 device drone. The rafts were moored in the open ocean by the Navy task group in water as deep as 3 miles. Late in October, after the last airdrop test device had been tested, the series was pronounced a success, both in refinement of weapon design concepts developed in the pistol test, and in further confirmation of the feasibility of the airborne diagnostic method for future testing. With Operation Dominic complete, the test
stuff would come in handy on a camping trip.
I'd a lot rather be at a camping trip. Say, what would they do if we have a base here?
At school they told us we should be away from windows and behind double walls. We don't want the inside hall.
Ted's right. If you live in an apartment house, you can't all go to the basement. Head for the shelter area. If none is marked for you, find cover away from windows and in the hallway if possible. Wait for the all clear. Be calm. If you're
Since that moment, the shadow of the atom bomb has been across all our lives. All men of goodwill earnestly hope that a realistic control of atomic weapons can and will be achieved. Meanwhile, good sense requires that all of us prepare for any eventuality. But wisdom demands, too, that we take time to understand this force. Because here, in fact, is the answer to a dream as old as man himself. A giant of limitless power at man's command. And where was it science found that giant? In the atom. A particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin. Just as other millions and quadrillions of atoms are the tiny building blocks which make up everything in the world. Ships, and shoes, and sealing wax, and cabbages and kings. Although no one has ever seen an atom, scientists have learned a great deal about how they behave, and there are widely accepted theories as to what they're like. Let's start by meeting a leading authority on the subject, Dr. Atom. Now, observing the professor himself, we can see that his structure resembles, in many ways, something almost as vast as the atom is small. The solar system. And there are certain similarities. Here is the center with electrons in surrounding orbits. But whereas the planet's movement of electrons is slightly different, there are other differences too. Hey, hold it! Thank you. Now, the solar system together is electrical. The electrons, which are negative, are attracted by the protons, which are positive, and vice versa. But here in the nucleus are other particles with no electrical charge called neutrons. Very important characters too, as we shall see. And equally important when it comes to atomic energy is what scientists call the atom's binding force. It's a kind of cosmic glue holding the nucleus together. This, then, is a single atom, but certainly not all atoms are alike. There are, in nature, more than 90 basic elements, which is science's term for families of atoms. To scientists, the atoms of the individual atom families, or elements, are identified by number. That is, the number of protons, or positive charges, in their nucleus. And they vary all the way from hydrogen, which has just 1 proton, to oxygen with 8 protons, to gold, he's rich with 79, finally on to the heaviest of all natural elements, uranium with 92 protons. Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes. Some elements, tin for instance, have a great many isotopes. Others, like aluminum, are lone wolves with just 1. Now, most atoms of most elements are content with their lot in life. We speak of them as being stable, but others are busy day and night, being what science calls radioactive. Like radium, throwing off powerful rays along with some of its neutrons and protons, until it actually alters its own nuclear structure and changes to another family, and then to another, until it does become stable at last. This spontaneous changing of elements is called natural transmutation. Its discovery gave men of science an idea. If an atom could change itself, why couldn't man change an atom? Using as bullets the very particles which radium threw off, a noted British scientist bombarded nitrogen and converted it to oxygen. In terms of individual atoms, this is what happened. The radium nucleus threw off an alpha particle consisting of 2 protons and 2 neutrons. the protons was absorbed into the nitrogen nucleus, turning it to oxygen. This was artificial transmutation, man changing the elements. From that first experiment, others by the thousands followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in two. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together. We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the two atoms into which a uranium atom splits also have binding force. But for some reason, it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission a million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But how to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb. At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission, the graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms, and here's what happens. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which converts the U-238 first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight.
However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air.
But perhaps the most valuable byproduct of the nation's reactor piles is radioactive isotopes. Research has revealed that many elements not naturally radioactive became so when placed in a nuclear reactor. And these isotopes, working as tracers with such measuring devices as a Geiger counter, became invisible detectives, aiding the cause of science in many different fields. In agriculture, isotopes are now used to test such things as the effect of fertilizers on plant growth and the proper timing for their use, helping to assure bigger and better yields from tomorrow's farms. In industry, isotopes have found literally hundreds of new uses, such as the automatic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible. In the fields of medicine and biochemistry, isotopes are performing near miracles of diagnosis and discovery. With radioactive sodium, doctors are solving more of the seeming mysteries of heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly simplify operations for their removal. Iodine-131 finds one of many uses in revealing conditions of the thyroid, and there are many more. New ways of using isotopes are being discovered constantly through the tireless work of modern pioneers in such fields as chemistry, metallurgy, medicine, and biology. Truly, the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, the destroyer. Another is the engineer, seeking to provide vast quantities of energy to run the world's machines. Another is the farmer, helping to better feed tomorrow's world. Still another is the healer, helping to diagnose and cure the sick. And the last is the research worker, working on in the fields of pure science to reveal more of the mysteries of the universe. But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age.
also minimizes radon-daughter ingrowth potential. The occupational hazards of lung cancer among uranium miners can be avoided, but never before in the history of mining has there been so great a need for management and employees to combat this problem. Control of this health hazard is within our grasp. We can and must meet this. study and evaluation before the final determination are made. With the first shot of the tumbler phase completed, we're taking the rest of the weapons north, some 10 miles across a ridge of mountains into the next valley, Yucca Flat, site of the buster operation. To try different heights at first over a completely different type of target. Stretching to the south, 12,000 feet from ground zero, are the various military effects measurement lines. The flash line here is basically a duplication of the Frenchman flat flash line. The target is a bullseye 500 feet across. By comparison with the lake bed in Frenchman flat, the surface in this area is rough and dusty. By comparison with data we got at Frenchman flat, we hope our instruments here will tell us if the thermal absorption characteristics of a target affect the shock wave. Here we will also get a valuable check on the effect of the height of burst on the development and effectiveness of the shock wave and Mach-wise depth. Tumbler, shot 2, 15 April 1952. The weapon for Tumbler, shot number 2, is the same size as the one detonated over Frenchman flat. Yield, 1 kiloton. Height of burst, 1,100 feet. This gave us a chance to detonate the same weapon over both the reflecting and non-reflecting targets. 22 April 1952. Tumbler, shot 3. Weapon yield, 30 kilotons. Height of burst, 3,500 feet. The same scaled height as shot number 2. These two tests would together provide an excellent check on the normal blast scaling law. To help the defense establishment produce their new height of burst curve, the Air Force dropped the weapon at a standard ballistic scale. Tumbler, shot 4, H minus 1 minute. Yield, 20 kilotons. Height of burst, 1,050 feet.
weapon system. In the normal development, production, and operation cycle, we usually take steps in series. By that I mean we carry out a study program, then a development test program, then we go into mass production before we finally introduce these weapons into the operational inventory. As a result, there
flying from one complex to the other and returning. We had intermediate range bombers of the B-47 type, which can fly from bases located on the fringes of the Eurasian complex to any point on that landmass. We also had fighter aircraft like the F-84 and F-100, capable of flying from Allied bases within Eurasia itself. Their range tremendously extended through air-to-air refueling. When missiles arrived on the scene, they began to augment the striking force of this kind of air power. ICBMs like Atlas and Titan, the intercontinental missiles, add to our long-range potential. An IRBM like Thor adds to our middle-range deterrent program. And a missile like Matador, with a range of several hundred miles, blends with our fighter force. For the immediate future, at least, the idea of combining aircraft and missiles mid-system seems like the ideal solution to defense. But not too long ago, 3 short years ago, we did not have this ideal concept. And so we flash back to Dateline, summer 1955, Washington, D.C.
In 1955, this is where we stood. We had fighter aircraft like the F-100, backed up by the Matador. We had begun the development of the ICBM Atlas and Titan to supplement the B-52. But we did not have an IRBM program to complement the B-47. We had a chink in our armor. We needed, and our NATO allies needed, a reliable IRBM as soon as possible.
Dateline, November and December 1955, Los Angeles, California. At this time period, there was already in existence in California a unit of the Air Research and Development Command. It was known as the Western Development Division. Later, the name was changed to the Ballistic Missile Division, referred to simply as BMD.
BMD was organized for one purpose and one purpose only: carry out a crash program on the development of the intercontinental ballistic missile. It was a unique organization spawned out of the creative talent of some of the nation's leading scientific minds.
BMD would eliminate red tape, shorten command and communication time, leapfrog development, and work concurrently on all phases of the problem.
When the need arose for an IRBM missile, BMD was already going full bore on the 2 previously assigned intercontinental missiles, Atlas and Titan. It was only logical that BMD also take on the development of an intermediate range missile, since it is generally the same kind of bird as an ICBM.
BMD was asked to get the IRBM program underway with utmost speed. As it turned out, it took 50 days, 30 days to submit plans, and 20 days to freeze design. This was the speed, the new look in Air Force research and development. This is how it was done. On the 28th of November 1955, BMD was directed to proceed to the IRBM. On the same day, contractors were notified to prepare proposals. These contractors were being asked to build an airframe, assemble the primary missile system, test the product, develop and fabricate ground handling equipment, and simultaneously create a manufacturing capacity to produce the number of completed missiles we needed in the time available. In short, these companies were handed a real headache. Those contractors who thought they could meet the stringent demands submitted their proposals. On December 23rd, the Douglas Aircraft Company was notified that it had been selected to assemble and test the Thor IRBM. On the 28th, Douglas signed the contract. During the remaining few days of 1955 and on into 56, the design of the Thor airframe was rushed to completion. On the 16th of January, the final configuration was released. The contractors for the other major components of the missile were already working for the Atlas program. General Electric would supply the nose cones for the new Thor. The AC spark plug division of General Motors would guide it. And North American's Rocketdyne division, the power factory. Thor was in business, backed by an all-star team, military, industry, and science. Dateline, April 1956, Douglas Aircraft Company. 3 months, the story of the creation of Thor has passed. Groundwork
military area's largest football field were being cleared. The great potential of American industry was beginning to stir. Missile technology was working up ahead of steam. It is strange that in this day of rare elements, alloys, and plastics, basic layouts often start with man's oldest material, wood. Thor was first a creature of wood, a skeleton of time, which engineers could investigate and experiment, fit and refit, check and recheck. But the missile itself was not the only item that had its beginning in wood. Scale models were made to check the feasibility of airlifting Thor in existing cargo aircraft. Perhaps designers are only boys at heart. The same serious, intense concentration is evident as they play with these toys. But a toy, if it's good enough, can give valuable insights into real problems, clearance, balance, weight distribution. The entire concept of a Thor weapon system from the start was that it must be air transport. Dateline, July 1956, Edwards Air Force Missile Test Center. 6 months have passed. Out on the California desert, test stand to check out the performance of rocket engines for being ready. The fact that these stands exist at this time points up the overlapping nature of the Air Force's ballistic missile program. These stands had been built for the testing of Atlas engines. Since Thor would use one of the booster engines from Atlas, these stands could be used for both studies. During the summer of '56, the first in a long series of engine tests was run. Power that would push Thor 1,500 miles through space within the system. Dateline, August 1956, Los Angeles, California. Thor was taking on shape and substance. Assembly line methods, reminiscent of aircraft production, were transforming Thor from raw concept to finished product. Giant presses conformed sheets of metal. Welding machines joined metal to form the characteristic cylindrical shape of a ballistic missile. Some 8 months from zero start, Thor was being produced in such a manner that future operational missiles could come off the same assembly line without major redesign of airframe, guidance unit, engine, or nose. Dateline, November 1956, Cape Canaveral, Florida. 11 months have elapsed. During these months, the Missile Test Center at the Cape has been ready to receive Thor for test flight. A launch pad is ready. A service tower is ready. A controlled blockhouse is ready. The range is ready. And in 11 months, the first Thor, Missile 101, arrived. Or the missile arrived in the way intended, by air. Out of the C-124, Thor, for the first time, rolls over the ground and will witness it file by file. And so, during the closing days of 1956, Thor follows the script and moves into dress wear. Thor is erected into its service tower. This is like a child being raised by proud parents on his first tottering steps. You have done your best in bringing up your offspring. Now it's up to him. However, such thoughts carry only so far. The missile is not a child. It is a mechanical giant. For one thing, it has to be fed thousands of gallons of liquid oxygen, which is only a fluid at the unbelievably low temperature of minus 297 degrees Fahrenheit. At last, Thor is fed and primed and ready. Ready, however, not for a flight, but for a static, a held-down test of performance. And Thor does perform, but not to the standards demanded. And before Thor can be ready for a full flight test, the year ends. 1957. 1 year of the story of the development of Thor has passed. We begin the new year at Cape Canaveral. During 1957, 10 missiles were fired from the launch pads of the Atlantic missile range. First was Missile 101, same Thor given a static test in 1956. The elaborate countdown was started during the day, carried on into the night.
Black Valley Route Road,
September 20th, 1957, Missile 105.
Clear attention in the blockhouse, please. Attention in the blockhouse. We're T-minus 35 minutes and a hot run. We're at T-minus 35 minutes and a hot run. Close the blockhouse doors. Close the doors. We're counting at T-minus 35. Man your stations. No talking, please.
Again, the launch area was clear. Instrumentation focused on the missile, and the countdown carried on to fire. This missile fired was a success. 1 year and 9 months from scratch, Thor came away. During the remainder of 57, 5 more Thors were fired. The first of these was a phase in a spectacular way. The other 4 missiles tested were successful, and as confidence grew, each firing became more ambitious. One of these flights exceeded design range by 900 nautical miles. Ample cause for real backslapping in the Thor blockhouse. While early missiles were merely stabilized on an approximate trajectory, now the missile's own guidance system was phased in to steer the missile precisely to target. At year's end, the score added up to 10 missiles fired, half of these very successful. Very creditable showing with missiles barely off the ground. But while flight testing was a real highlight, of equal importance in 1957 was the preliminary work being done in planning for an operational capability. One idea dominated things. A missile, no matter how good, is useless unless it can be handled easily and effectively by the military in the field. Step number 1 was to work in diagrams, almost an artist's concept of what an operational site would look like. This was the first visualization. Diagrams merged into scale models of launch and trailers, fuel cells, and transfer systems. In short, all spec features of ground handling a new tool of work. This was the second visualization. Scale models then came to life in full-size units. A real prototype launcher was constructed. Fuel storage tanks were fabricated. Trailers were equipped with checkout and control equipment, pressurization grills, power trailers. All of these real units moved into a demonstration area and were set up to roughly conform to the planned field installation. And the key men of the project came out to look and observe. This was a place to inspect, but it was also a place to imagine, to evolve new ideas and generate improvements prior to final design freeze. So 1957 came to a close, with Thor pointing its nose to the sky in an operational environment. This was the backyard of a factory, but it was symbolic of events that would happen in the backyards of the world. Dateline, January 1958, Missile Test Center, Florida. C-133 is at the gate with the new launch equipment aboard. Shortly thereafter, it is being tested in preparation for a flight test. Dateline, January 1958, Sacramento, California. Concurrent with events in Florida, on test stands in California, other missiles were being captive tested to learn something additional on such factors as vibration, duration of thrust. Dateline, February 1958, Edwards rocket base. Other Thors on test stands. Simultaneous feedback of information is at work. Here at Edwards, data will be gathered on environmental factors affecting Thor. A missile in the field may have to withstand Arctic cold, tropic heat, driving rain, sleet, and snow. You cannot make Thor an all-weather missile by guessing. You must test and know. Dateline, May 1958, Santa Monica, California. By this time, operational type missiles are coming off the assembly line in a steady flow. The soundness of basic design and production line tooling are paying dividends. Not only missiles, but all of the support equipment associated with it are also in quantity. no flight readiness cycle. This time, Thor will be fired forward in the case of true operational use. And the flight is a success. Thor takes off as well from this simplified tactical launcher. It has some more elaborate R&D test launches. Dateline June 1958, Tucson, Arizona. A new and vital facet has become a part of the program. Training. Training is simple logic. Mastery of arms has been with us ever since man threw the first spear, fired the first crossbow. Here today, men from the United States Air Force and from England's RAF master the specialized techniques of handling and firing a ballistic device. The diploma testifies that they are now missilemen. More specifically, missilemen capable of carrying out a new idea in defense, the IRBM idea. Dateline, September 1958, somewhere over the Atlantic. The significance of this aircraft flying the Atlantic is that it carries in its cargo compartment the first Thor to be delivered to an overseas base. Thor rolls quietly through the English countryside. 2 years and 9 months from inception, an IRBM missile is in the hands of one of our NATO partners. 2 years and 9 months. Streamlined development for the ballistic missile age is a fact. 1958. Over 17 years since the battle of Britain. Then the people looked to the Spitfire, Hurricane. Today, a new protector guards their shores. Dateline, late summer, 1958, Cape Canaveral range. By this time period, the use of the Thor weapon system has assumed wider proportions. Thor has another missile stage fitted to its nose section. It becomes Thor Able, a new type of re-entry test vehicle. This vehicle is capable of hurling a nose over the ICBM range of 5,500 nautical miles. In other words, Thor Able can, at full range and with realistic velocity, gather data to check whether an ICBM nose cone is correctly designed. Thor Able becomes a valuable test instrument. It allows ICBM data to be collected by a smaller type missile, thereby allowing more flight test time for an ICBM like Atlas. Another example of the integrated ballistic missile program. Dateline, the Moon, summer and fall, 1958. During this time period, Thor became one of the vital stages in the Air Force Space Probe project. For the Space Probe, 3-stage missiles were assembled. Thor was the main stage, the prime propulsive package. Of the 3 attempts, the second try made in October of 58 was the most successful. This time, all 3 stages functioned nearly perfectly. The vehicle was optimized to 2.5-day journey. A slight deviation in control put the missile off course. The terminal vehicle traveled more than 71,000 miles towards the moon before returning to Earth. While attempt number 2 did not achieve all objectives, much urgent information was obtained. This was the first real look at the Earth's magnetic field and at temperatures and radiation levels from 70,000 miles up. This missile attained a higher speed and went a greater distance than any vehicle before it. Dateline, December 1958, Vandenberg Air Force Base. This new missile base on the coast of California is the site of another one of Thor's ambitious undertakings. The Discoverer satellite will be fired in polar orbit, which will be the first time the South Pole to North Pole path has been used by any of the man-made moons. Early in '59, the first of these satellites, a 1,300-pound unit, was successfully put into orbit. Yes, with the versatile Thor as one of the prime tools, man in '58 was pushing back the frontiers of space. Doing this with a missile that did not even exist 3 short years before. 3 short years. Speed of development being ready now is the big story of Thor. If the need should arise, operational Thors can be uncovered, fused, directed, and fired within 15 minutes.
high-yield weapons. As an example, there has been much uncertainty in specifying the minimum safe distance for aircraft delivering high-yield weapons. Blast and thermal effects were measured on B-36 and B-47 aircraft, positioned so that some damage was expected. This data will help us to specify the yield at which parachute drops are required for delaying a detonation, as well as providing us with answers to many questions which arise when positioning for multiple drops is considered. The whole picture of fallout contamination becomes of increasing importance to high-yield weapons. In one program, drone ships were sent into fallout areas to evaluate the work of the washdown system for ship decontamination. We found we could measure fallout even in large ocean areas by making aerial surveys using extremely sensitive radiation detection equipment.
final shot of Operation Castle. This device was also flown out to the forward area for final assembly at Perry Island. Charge was towed directly to its zero point at enemy target Atoll. Here, over the spot that was once the island of Kaluja Lab, and is now the right crater, was anchored in position. At 6:20 on the morning of May 14th, the smallest device of the operation was ready. This test initiated an investigation of small, lightweight thermonuclear weapons in the megaton class. Size of picture is 14 by 18 miles. The yield was about 1.7 megatons, essentially as predicted. From this firing, we learned that we had the capability of developing megaton weapons weighing less than 10,000 pounds.
One complete transformer substation has been erected relatively close to the shot tower. The second substation and power lines have been placed at a much greater distance from the tower. Two kinds of radio towers are to be tested. One tower is self-supporting without guy wires, and the other has supporting cables. Both types are very common. Nearby, a complete radio transmitter will actually broadcast from tape before the shot to be picked up by radios in the test towers. Both liquefied petroleum and natural gas facilities will be tested. Our questions: will the fittings and connections stand the test? Will there be fires? All equipment is installed and checked by experts from the LP Gas Association and the American Gas Association. This is an 18,000-gallon supply tank, partially filled with propane, and complete with feed pipes. Here, a weighing and storage house and delivery platform have been erected on the test site.
I was eager to learn all I could about the various types of houses to be tested.
5 types are to be exposed to the blast and heat of this atomic explosion. First, a single-story frame rambler without basement, built on a concrete slab. Second, a 2-story masonry home with basement, constructed of brick, backed with 4-inch cinder block. Third, a house of 8-inch concrete blocks reinforced with steel. A fourth is a single-story rambler made of precast lightweight concrete. Walls and roof panels are joined by steel lugs. The fifth, at a 5,500-foot line, is a house similar to one previously tested in 1950, but a new design provides additional strength at a cost increase of approximately 10%. That's the real purpose of testing these houses, to find their weak points.
Through the cooperation of the furniture and appliance industries, household furnishings were installed in the houses. Mannequin families were supplied by private industry. Interior home furnishings, also donated by industry, were complete in every repair. Textiles and synthetic fabrics were also to be tested.
Rows of mannequins are set up in the open facing the blast. Each item of clothing and each color has been carefully selected.
As a mother and housewife, I was particularly interested in the food test program, a test that included canned and packaged foods.
Some foods are to be tested in the house, stored in the usual way. Other foods, including fresh meats, butter, and similar perishables, are to be tested just below the level of the ground at 3 positions along the main test line. This will expose the food to high-intensity radiation without risking destruction of the containers. Test items include sterilized foods packaged in cartons, metal, and glass. All will be exposed according to plan to give us the most information.
The night of the actual explosion, or rather early in the morning, finally came. On Media Hill, television equipment was positioned. Reporters, commentators, military and civil
masonry house that was not reinforced. This is the house constructed of reinforced concrete blocks after the explosion. Although the redesigned two-story frame house was severely damaged, the structural improvements had strengthened its resistance considerably. The basement shelter had offered some degree of protection. The reinforced bathroom shelter was standing intact beneath the ruins of the house, so this type also offered some degree of protection. The upper section of one unguided radio tower collapsed from the tremendous force of the blast. The guide tower was slightly twisted by a power pole which fell across one of the guy wires. Within the concrete radio house, equipment had been shaken up, but as soon as power was restored, the transmitter resumed broadcasting. The 18,000-gallon tank of liquefied petroleum gas was undamaged. The connections were intact. The weighing and storage house was scattered across the desert, but the consumer-sized tanks were unharmed. Power lines and transformers suffered some damage, but most of the power poles were still standing, or could be repaired. The power substation was not seriously harmed. Edison Institute experts tested all lines and found the station to be operative. The food and cases of canned goods were taken away for laboratory tests.
A tattoo mark was left beneath the dark pattern of this dress. The blast charred and faded the outer layer of this dark suit. During all this activity, the mass feeding group had been improvising to feed the test observers. These cans could have been salvaged from demolished buildings and used for preparing meat. As I watched the people eating, I realized that mass feeding would be an important job for civil defense. I took a last look at the debris and devastation. This time, it was only a test, a well-planned test, not a real attack. It was a test of the things we use in everyday life.
Multi-megaton weapons would result in much greater damage over a larger area. But many lessons were learned from this test that have affected civil defense planning. All these factors must be considered as we plan for the survival of our homes, our families, and our nation in the nuclear age.
their way through Las Vegas, the big guns experienced no trouble whatsoever in negotiating the city's fleet. On the sharpest of turns, however, is where they really proved their mettle. Handled exactly like the biggest hook and ladder trucks of any fire department, but some 30 feet longer and many tons heavier, the guns together twist and turn in stride. They are big, but flexible. Once out of Las Vegas, they settle down to the long grind north to the proving ground. During field operations involving the 280mm gun, they travel in batteries, such as these. A battery consists of 2 guns. 3 batteries make up a battalion. The battalions provide support for field armies or separate corps actions. There are, with each battery, 9 support vehicles, acting as transport for gun personnel, supplies, and ammunition. In convoy on the hard-top highways, the guns can travel at 30 miles per hour, and in spite of their road weight of 76 tons, can use the standard Army bridges wherever necessary. 70 miles north of Las Vegas was the turnoff to the firing site. In 1944, when the original design specifications were drawn up, the gun was to have been a 240mm weapon. However, these specifications were soon changed by the rapidly advancing artillery capabilities and the foreshadowing of the atomic age. Instead, we substituted the designs for a 280mm weapon, with not only HE, but atomic firepower. In 1951, the gun was tested as a normal artillery piece at Aberdeen. Needless to say, these tests were successful. All that remained was to check out its other capabilities, the atomic shell. Even on secondary roads or rough terrain, the guns retain relatively high mobility in spite of the fact that their speeds are lowered to approximately 10 miles per hour. The main reason for this mobility are the prime movers connected to the front and the rear of each weapon. Each prime mover is capable of 365 horsepower. Just one of these cabs has 50% more payload than the largest Western highway trucks. For a heavyweight fighter, the big guns are light on their toes. Once at the firing site, the line of fire was given, and the guns were directed to their respective emplacements. After getting into position, the rear cab lowers the gun and moves away. Then the front cab rinses the tube into battery and moves away. Unlike field operations of World War II, these guns need no extensive ground separation. In most cases, there is no necessity for excavation of any kind. The entire 47-ton weight of the gun itself is balanced by a turntable and 3 jacks to hairbreadth specifications. The total time to prepare for firing, just 20 minutes. After being placed in their firing positions, and prior to the firing of the Mark 9 atomic shell, a series of HE rounds were fired. These rounds serve the purpose of a final check on the many ballistic variables which could affect the accuracy in a given situation. Unlike the standard artillery weapons, which are single recoil mechanisms, the 280mm gun has the advantage of a double recoil action. When fired, the tube recoils into the upper carriage, and then the upper carriage recoils. Such a system is the main reason for the lack of ground separation folding trough is used to load the projectile and the propeller. During firing operations, ramming can be done both manually and hydraulically. The gun is capable of a 360-degree traverse and can go to a maximum elevation of 55 degrees. The time for rehearsals and final checkout is over now as 0 hour approaches. The big gun is ready to prove its atomic punch with the firing of the Mark 9 shell as one phase of Operation Upshot and Upward in the Nevada desert. Everything functions with a precision found in any capable, well-trained team. 0 hour is minutes away now. The projectile is prepared and brought to the gun. The final correct setting for time of burst is made. The breech closed and the primer inserted. Once loaded, the gun's elevation is set with a gunner's quadrant. Sighting is done with a panoramic telescope. As the last step, the primer is connected and continuity of timing and firing circuit is completed between the control point and the firing site. With everything set now, the gun crew moves back to take positions in slip trenches during firing. The time is 0830. The date, 25 May, 1953. With a degree of accuracy 4 times greater than any gun developed before World War II, the 280mm gun has proven its worth. Capable of delivering the atomic shell some 13 miles under any weather conditions, day or night, the big gun provides more accurate and damaging support to ground troops than any other gun in the recorded history of warfare. Exceedingly powerful, but flexible, and with a high degree of mobility, the 280mm gun is one of the Army Field Force's newest tactical weapons.
Chairman Mao said, let those internal and external reactionary fleets face us in trepidation. When they say that this cannot be done, and that cannot be done, ignore them. With indomitable and indefatigable effort, the Chinese people will steadily attain their objectives. The sun rises from the east every morning with rosy rays in myriad shapes. Our great socialist fatherland is in a... Our great teacher, great leader, great commander, and great helmsman, Chairman Mao, is the red sun in our hearts. Under the leadership of Chairman Mao and the Chinese Communist Party, under the guidance of the general line for socialist construction of the party to strive hard and strive to advance, and to get greater, faster, better, and more economical results, and under the three great movements of class struggle, production struggle, and scientific testing, our Chinese people have achieved great successes. Our nation's people's communes are further developing and consolidating. In the wide countryside, there is revolutionary outlook everywhere, and there is laughter everywhere because of bumper crops. They sing, learn how to do things on a large scale, and have the courage to do things on a large scale. Gather the red flowers which are blooming everywhere on a large scale. The broad masses of workers on the industrial war front are fiercely engaged in revolutionization and fiercely breaking loose from foreignization to choose their own industrial development path. They are applying maximum effort. They dare to apply maximum effort. This spirit of applying maximum effort is prevalent throughout the whole nation. Throughout our great fatherland, the heat of revolution is generating everywhere, and a new all-around leap-forward situation is emerging. Our national defense industry, under the correct leadership of the party's Central Committee, the great leadership of Chairman Mao, Comrade Lin Bao, the post-war buddy of Chairman Mao, and Comrade Zhou Enlai, is progressing at 1,000 li a day. Preparations for our nation's first nuclear test are intensely underway. Mao Zedong's thoughts guide us in all our work. In response to Vice Chairman Lin Bao's call, the comrades raise high the great red flag of Mao Zedong's ideology, creatively study and apply Chairman Mao's work, and apply themselves vigorously. Servicemen in the engineering corps, braving bitter winds and sandstorms, are struggling day and night, overcoming difficulties to erect various buildings and installations for the explosion. Scientific and technical personnel, even with crude instruments because of the lack of sophisticated instruments, are carrying on preparatory work in chemical analysis. Our nation's broad masses of workers, engineers, technical personnel, scientists, and officers and men of the People's Liberation Army all energetically put their efforts together to make a large quantity of instruments and equipment. Here, the various instruments are undergoing a final check before the test. These instruments laid out on the site will accurately record the various results of the test. We not only must have our own atomic bomb, but we must, under the threat of the enemy's atomic bomb, acquire the capability which we should have to destroy the enemy and the knowledge to preserve ourselves. The comrades ready for the test are intensely engaged in training activities. Fighters armed with Mao Zedong's thought are not deterred by any difficulty. For training, they pick the hottest time in the day to march in boiling sand. In each training session, how much sweat do they perspire? During the intense struggle, they always maintain the glorious traditions of our Army, resolutely struggling in spite of hardships and displaying the cheerful revolutionary spirit. Comrades of the cultural and arts troops penetrate deeply into the area to conduct propaganda and stimulating activities. The comrades, using discarded lumber to make poles and grass strings to weave a net, engage in mass physical exercise. In the whole test area, the atmosphere is enveloped with a spirit of unity, tension, solemnity, and animation. Comrades of the Quartermaster Corps are delivering supplies straight to the door with the single purpose of servicing the whole front wholeheartedly. Streamlined trains reach the site and sewing machines are moved to the barracks. The testing day is approaching, and all types of equipment and arms for testing are transported to the site. In this testing, not only will all kinds of testing equipment and installations be used to measure the magnitudes of the atomic bomb, but 4 categories of equipment and installations for national defense, engineering, animals, and civil defense will be subjected to testing. At 1500 hours on October 16, 1964, the event which shocked the whole world finally takes place. the levels of the first nuclear tests of the United States, Britain, and France. This is the result of the efforts of our nation's workers, engineers, technical personnel, scientists, officers and men of the People's Liberation Army, and all those concerned who willingly raised high the great red flag of Mao Zedong's thought, gave prominence to politics, creatively studied and used Chairman Mao's work, and concentrated their efforts to wage a battle of annihilation with united and vigorous cooperation. This is a gigantic success of Mao Zedong's thought. This is a gigantic success of the General Line. Long live the Chinese Communist Party. Long live Chairman Mao. Personnel and cars entering the contaminated area of the explosion for recovery work are given strict examination. These women comrades are glad to join the ranks of combat. Entering the contaminated area is an intense battle of racing against minutes and seconds to complete the task. Chairman Mao says, in our work, we must be enthusiastic but calm, and intense but orderly. See how intensely and earnestly they attend to their work. They successfully returned. The people greet them intimately and warmly. In the afternoon of October 16, 1964, Senior Shows announces the news about our nation's successful experiment in testing its first atomic bomb. The nuclear monopoly and nuclear tyranny of the U.S. imperialists and the revisionists have been thoroughly bankrupted. Their criminal attempts to block and prevent our nation's people from grasping nuclear weapons have been thoroughly smashed. Work for the second nuclear test is begun. The comrades, not fearing hard labor and fatigue and continual fighting, are eagerly engaged in the new battle. The combat teams are given pre-combat political indoctrination to prepare for an intense struggle maneuver. At present, the U.S. imperialists are shifting their warlike strategy to Asia. They are maniacally expanding the war of aggression in Vietnam, and they are preparing to impose war on the heads of the Chinese people. Chairman Mao says, the imperialists have humiliated us so severely that we must seriously take them to account. We must be prepared to fight early, to fight on a large scale, to fight great nuclear war, to fight all kinds of war, and on several fronts. Another stimulating and jubilant day arrives on May 14, 1965. Our nation successfully explodes the second nuclear bomb in the sky over the western part of our country. This is an extremely accurate and extremely successful explosion. This demonstrates the great results of cooperation among leaders, specialists, and the masses, and of the cooperation of education with research. This is another victory song for Mao Zedong's thought.
这是领导、专家和行动相结合，教育、研究、生产相结合的伟大成果。这是毛泽东思想的又一曲凯歌。
To gain military experience under atomic conditions, the various tactical and maneuvering units enter the area of the explosion to conduct tactical maneuvers. Following Chairman Mao's teaching, they go forward without fear of sacrifices to overwhelm difficulties and grasp victory. Chairman Mao has always taught us that weapons are an important factor of war, but they are not the decisive factor. The decisive factor is not material, but man. Vice Chairman Lin Dao points out that under nuclear conditions, the greater the power is, the more intense the close fighting and night fighting will be. Regardless of offensive or defensive, the final decisive battle will be won at close combat at 100 or 200 meters. At that time, it will depend on who is tougher, who can take a position, who can hold it, who dares to see red on his bayonet. At that time, it will depend on one's proletarian consciousness and one's courage. We have the spiritual atomic bomb, which is impossible for the enemy to acquire, and we also have the material atomic bomb. No enemy can defeat us. If the imperialists dare to impose war on our heads, we will finally break the sinews and bones of the aggressors and thoroughly and completely destroy all of them. After the successful second nuclear testing, work on the third nuclear testing site. Comrades on the testing site resolutely pursue the working styles of 4 firsts and 3 eighths. The political air is thick in the entire testing area. Read Chairman Mao's book. Obey Chairman Mao's book. Follow Chairman Mao's principles in doing so, and be a good fighter for Chairman Mao. This becomes the common behavior of all the comrades on the testing ground. They always carry Chairman Mao's works with them and study them everywhere and anytime. They resolutely and thoroughly implement the directives of Vice Chairman Lin Dao on giving prominence to politics and the 5 principles. They study hard and apply their knowledge to their work. Here the cadres and servicemen are exchanging their experiences in the creative study and use of Chairman Mao's work. They realize that Chairman Mao's sayings are honest, most powerful, every sentence contains truth, every sentence is worth 10,000 other sentences, and Mao Zedong's thought gets results when applied in any situation. The kitchen comrades also put forth their efforts for this nuclear test. sandstorm and the howling wind, how turbulent they are, and the skies and earth, how dark they are. But who cares? No matter how great the difficulties are, they cannot be greater than the determination of fighters who are armed with mouth-between thought. They, from the beginning to the end, resolutely stay at their fighting post. Chairman Mao says, the Chinese people are not even afraid of death. How could they be afraid of difficulty? Comrades, cadres, and fighters, following Chairman Mao's teachings of the spirit of the foolish old man who moved the mountains, are working together intensely to complete great engineering work. Remembering Chairman Mao's teachings, blend their sky-high revolutionary fervor with their scientific attitude to strictly check all types of instruments and installations. These are the materials and equipment for civilian uses to be tested. They are preparing the different animals for participation in the test. Stimulating time, 1,600 hours on May 9th, 1966, will soon be here. Explosion of our first atomic bomb to the successful explosion of our first thermonuclear bomb, it took us only a little over 1 year. Such great leap forward progress proves that the Chinese people, equipped with mouth-between thought, dare to take a road never before taken by their predecessors, dare to scale a peak never before scaled by their predecessors, and are able to equal any miracle done by anyone else. since defense against nuclear weapons is possible. Look at these two dogs underground. They are much safer than those dogs on the surface. They had only an iron plate coated with lime over them. After the explosion, they are not harmed by the radiation. These chickens even laid eggs after the nuclear explosion. The monkeys in the sheltered headquarters leaped only once when the fourth explosion occurred. There is no damage to the electric lights and electric wires in the sheltered headquarters. The sheltered headquarters is adequate protection against atomic attack. The exposed buildings on the surface are seriously damaged, but the nearby semi-underground buildings are in good condition. The earth, scorched by the explosion, can still nourish plants. The seeds exposed to the explosion can still germinate and grow. Damaged crops can live and even grow luxuriantly. Khrushchev and his divisions recklessly said that the atomic bomb would destroy all mankind. This is nothing but a devilish lie. They just want to bully the revolutionary people with their nuclear bombs. We proudly received the wonderful news. Victory belongs to the great, glorious, and corrupt Chinese Communist Party. Glory belongs to our most beloved Chairman Mao. Chinese people and the Chinese government will, as they always have continuously, unswervingly struggle together with all the peace-loving peoples and nations in the whole world, and for the lofty goal of all our prohibition and thorough destruction of all nuclear weapons. The morale of the revolutionary people in the whole world is bolstered by the successful capability of the Chinese people to control nuclear weapons. This punctures the pride of the imperialists, the neo-revisionists, and the reactionary cliques of various nations. For this, we have received numerous felicitations from fraternal parties, friendly countries, government leaders, people's groups, and enlightened personages, congratulating us on our great achievement in the third nuclear test. They cheer fervently because the nuclear weapons in the hands of the Chinese people are ones to be used for the protection of world peace, for inspiring the revolutionary people in the world to struggle against the United States. This is a victory of Mao's determined cause, and the victory of the general line. Shout aloud with fervent emotion. Sing aloud with fervent emotion. must always remember Chairman Mao's dictum. The atomic bomb is a paper tiger used by the U.S. reactionary fleet to frighten the people. It appears ferocious, but actually it is not. Of course, the atomic bomb is a large-scale, mass-killing weapon. But what decides the outcome of a war is not one or two new weapons, but the people.
Productions Incorporated. Hey, Bert, come on out and meet all these nice people, please. Oh, all right. We really can't blame you. You see, Bert is a very, very careful fellow. When there's danger, this is the way he keeps from being hurt. Sometimes it even saves his life. That's why these children are practicing to duck and cover just as you do in your school. We all know the atomic bomb is very dangerous. It may be used against us. We must get ready for it, just as we are ready for many other dangers that are around us all the time. Fire is a danger. It can burn whole buildings if someone is careless. But we are ready for fire. We have a fine fire department to put out the fire. And you have fire drills in your school so you know what to do. Automobiles can be dangerous too. They sometimes cause bad accidents. But we are ready. We have safety rules that car drivers and people who are walking must obey. Now, we must be ready for a new danger, the atomic bomb. First, you have to know what happens when an atomic bomb explodes. You will know when it comes. We hope it never comes, but we must get ready. It looks something like this. There is a bright flash, brighter than the sun, brighter than anything you've ever seen. If you are not ready, did not know what to do, it could hurt you in different ways. It could knock you down hard, or throw you against a tree or a wall. It is such a big explosion, it can smash in buildings, knock signboards over, break windows all over town. But if you duck and cover like Bert, you will be much safer. You know how bad sunburn feels. The atomic bomb flash could burn you worse than a terrible sunburn, especially where you're not covered. Now, you and I don't have shells to fall into like Bert the turtle, so we have to cover up in our own way. First, you duck, then you cover, and very tightly cover the back of your neck, your face. Duck and cover underneath a table, or desk, or anything else close by. In Betty's school, they're talking about the atomic bomb too. Betty is asking the teacher, how can we tell when the atomic bomb may explode? The teacher is explaining that there are two kinds of attack, with warning and without any warning. We think that most of the time we will be warned before the bomb explodes, so there will be time for us to get into our homes, schools, or some other safe place. Our civil defense workers, our men in uniform, will do everything they can to warn us before enemy planes can bring a bomb near us. You may be in your schoolyard playing when the signal comes. That signal means to stop whatever you are doing and get to the nearest safe place fast. Always remember, the flash of an atomic bomb can come at any time, no matter where you may be. You might be out playing at home when the warning comes. and cover fast, wherever you are. There's no time to look around or wait. Be like Bert. When there is a flash, duck and cover, and do it fast. Here are some older boys showing what to do if the flash comes when you are not in the plant. This is what to do to be in a corridor. Duck and cover tight against the wall this way. Remember to keep your face, the back of your neck, covered tightly. Try to fall away from windows or doors with glass in it. Then, glass breaks and flies through the air, it won't cut you. You might be eating your lunch when the flash comes. Duck and cover under the table. Then, if the explosion makes anything in the room fall down, it can't fall on you. Getting ready means we will all have to be able to take care of ourselves. The bomb might explode when there are no grown-ups near. Paul and Patty know this. They are always ready to take care of themselves. Here they are on their way to school on a beautiful spring day. No matter where they go or what they do, they always try to remember what to do if the atom bomb explodes right then. It's a bomb. Duck and cover. Paul and Patty know what to do. Paul covered his acting cap so that he wouldn't be burned. And Patty covered herself with a cloak she was carrying. They knew how to duck and cover. They acted right away when the flash came. If they had been at this doorway when the bomb flashed, Paul and Patty would have ducked and covered this way, like this girl. Heavy doorways are a good place to duck and cover. She will be safer too. Here's Tony going to his Cub Scout meeting. Tony knows the bomb can explode any time of the year, day or night. Get ready for it. Duck and cover. Atta boy, Tony. That flash means act fast. Tony knows that it helps to get to any kind of cover. This wall was close by, so that's where he ducked and covered. Tony knew what to do. Notice how he keeps from moving or getting up and running? He stays down until he is sure the danger is over. The man helping Tony is a civil defense worker. His job is to help protect us when there is danger of the atomic bomb. We must obey the civil defense worker. We must know how to duck and cover in the school bus or in any other bus or streetcar. Duck and cover. Don't wait. Duck away from the windows fast. The glass may break and fly through the air and cut you. Sundays, holidays, vacation time, we must be ready every day, all the time, to do the right thing if the atomic bomb explodes. Duck and cover. This family knows what to do. Your own family should. They know that even a thin cloth helps protect us. Even a newspaper will save you from a bad burn. And the most important thing of all is to duck and cover yourself, especially where your clothes do not cover you. No matter where we live, the city or the country, we must be ready all the time for the atomic bomb. Duck and cover. That's the first thing to do. Duck and cover. The next important thing to do after that is to stay covered until the danger is over. Yes, we must all get ready now, so we know how to save ourselves if the atomic bomb ever explodes near us. If you do not know just what to do, ask your teacher when this film is over. Discuss what you could do in different places if the bomb explodes. Older people will help us as they always do. There might not be any grown-ups around when the bomb explodes. Then, you're on your own.
Remember what to do, friends. Now tell me right out loud. What are you supposed to do when you see the flash? Duck and cover. Duck and cover. Duck.
В соответствии с программой испытаний новых образцов водородных зарядов 30 октября 1961 года был произведен взрыв чистой водородной бомбы с тротиловым эквивалентом 50 миллионов тонн. Новый водород водородный заряд разработан большим коллективом ученых, конструкторов и изготовлен на предприятиях министерства. При испытаниях заряд был смонтирован в корпусе авиационной бомбы, способной вмещать заряды мощностью 100 миллионов тонн и более. Взрыв намечалось произвести на большой высоте над землей с использованием самолетов. В хвостовой части бомбы предусмотрено место для установки парашютного устройства. Для транспортировки в собранном виде изделие было помещено в особый железнодорожный вагон. Стенки и крыша вагона разборны. Место назначения изделие было направлено к летальному поезду. При следовании поезда были приняты все необходимые меры безопасности. Для подготовки бомбы к испытаниям и подвески ее к самолету был выбран один из аэродромов дальней авиации военно-воздушных сил, расположенный на польском полуострове. Сюда прибыл поезд с изделием. На железнодорожной станции аэродрома хорошо оборудованная погрузно-разгрузочная площадка. Все разгрузочные операции производились по намеченному заранее регламенту. После завершения разборки вагона к железнодорожному составу подан автомобильный поезд. И изделие было перегружено на автоцех для дальнейшей конструкции. Проверка и подготовка изделия к испытанию производилась в специальном здании. Здесь детальному и строгому техническому контролю был подвергнут каждый узел изделия, каждый элемент его автоматики. В момент срабатывания заряда имеют значение даже миллионные доли секунды. Поэтому элементы автоматики, телеметрические датчики и передающие устройства должны быть настроены на заданную программу с абсолютной точностью. Проверка узлов изделия подходит к концу. Устанавливаются на свои места съемные части бомбы. Закрываются люки. Последний общий осмотр. Результаты многотонных приборов самостоятельно нет. Снаружи прикинет кинокамеры для съемки время взрыва. Устанавливали калориметр для замера тяжести. Узел связи его сооружение. Пункт радиотелеграфной связи. Аппаратура для радиотелефонных переговоров. Автоматическая радиостанция – одна из самых мощных потерь в нашей стране. Все это позволило организовать систему надежной дозированной связи между пунктами, обеспечивающими проведение испытаний, которые находились на значительном расстоянии перехода. Государственный испытательный полигон номер 6 Министерства обороны Казахстана, опыт, расположен район Белушки, основная база полигона. Здесь размещается штаб научников, институтов, лаборатории и вспомогательных структур. На период испытаний Белушки была сосредоточена группа трудов трудового обеспечения. Объединенный командный пункт руководства испытаний находился в подземном сооружении. Здесь большой радиотелеграфный и радиотелефонный пункт. Его задача входила поддерживать двустороннюю связь с пунктами, расположенными на территории полигона, с аэродромом на Кольском полуострове, самолетом-носителем во время его полета. Расстояние от командного пункта в Белушке до опытного поля 250 километров. Значительно ближе находилась площадка Д-8. От нее до поля 90 километров. Эта площадка использовалась для подготовки и управления автоматической исполнительной ионизирующей аппаратуры, размещенной в районе взрыва. Средством сообщения между площадкой Д-8 и опытным полем были военные самолеты. Оперативные переброски производились на вертолете. Площадка для сброса бомбы была выбрана в той части новой земли, где характер местности создавал наилучшие условия безопасности взрыва. В задачу испытания не входило изучение разрушительного действия данной волны. Поэтому мы не видим в районе опытного поля дальневоздвижных зданий, разве какой-либо военной техники. Вместе с тем, здесь было размещено большое число самых разнообразных аппаратур для регистрации и измерения параметров. Включение аппаратуры и установленные сооружения в области поля производилось автоматически по радио. Радиосигналы поступали с площадки Т-8. Без подземного движения находился командный пункт службы образования. Здесь был установлен программный автомат, выдающий команды на поле. Как же проходил основной этап? До взрыва осталось несколько часов. Белушный, начальник штаба полигона, принимает доклад о мерах, принятых по выполнению оперативного плана морского обеспечения. В этом плане точно определено, где будут находиться корабли и личный состав полигона в момент взрыва. Подготовка опытного поля закончена. Производится полная эвакуация личного состава кораблей в безопасную зону. Напряженно работает метеорологическая служба. Составляется карта прогноза погоды. Особенно тщательно изучается направление ветров. В боевой готовности служба противовоздушной обороны. Опасный район покидает ответный сигнал. Принято решение подвесить изделие самолета на снизу. Подвеска бомбы такого размера и веса совсем трудно. Но на аэродроме к этому хорошо подготовлены. Производится особенно тщательно проверяется укладка парашютной системы. От надежности ее работы зависит безопасность экипажа. Для подвески бомбы созданы специальные подъемные устройства. Подъем изделия к самолету идет плавно и равномерно. Размеры бомбы не позволяют разместить ее в бомболюбе самолета, поэтому она закрепляется выше до фюзеляжа. Заседание Государственной комиссии по проведению испытаний. Производится оценка общей обстановки, складывающейся в районе испытания по назначенному времени взрыва. Окончательно уточняется трасса и условия полета самолета. На новой земле еще раз проверяются условия безопасности от последствий взрыва для районов, расположенных вне территории испытательного полигона. Анализ данных, из которых складывается общая обстановка с момента взрыва, дает уверенность в том, что распространение ударной волны будет ограничено, а зона возможных разрушений поверхности минимальна. последнюю инструктаж. Командный пункт аэродрома. Приближается время старта. Разрешен запуск мотора. Заработали турбоинтовые двигатели. Лед разрешен. Следом за носителем в воздух поднимается самолет лаборатории. Самолет-носитель с подвешенной к нему особо мощной водородной бомбой набирает высоту. За ним ведется неослабное наблюдение в различных пунктах на Земле. С экипажем поддерживается непрерывная двусторонняя связь. Десятки локационных станций противовоздушной обороны следят за общей обстановкой в воздухе. Высота 10 500 метров. Экипаж самолета-носителя отлично подготовлен к выполнению ответственного боевого задания. На параллельном курсе самолет-лаборатория. Точно следуя намеченным курсом, самолеты приближаются к новой Земле. Теперь управление полетом и связь с самолетами передается командному пункту полигона. Сюда поступают доклады экипажей о ходе полета. Отсюда, по условным таблицам, передаются команды на самолет-носитель. Носитель вышел на боевой курс. Цель видна. Управление сбросом бомбы переводится на автоматику. Сигнал «Сброс». На Д-8 включается программный автомат аппаратуры опытного поля. «Сброс». Экипаж надевает защитные очки. Программный автомат принял сигнал «Сброс» и выдает команды запуска аппаратуры опытного поля. Точно по расчету сработала парашютная система. Бомба приближается к точке взрыва. Высота 4000 метров. Осталось 3 секунды. 2, 1, 0. Взрыв сопровождался световой вспышкой необычной силы. В этот момент самолет-носитель находился в 45 километрах от места взрыва. Вспышка и последующее свечение, несмотря на сплошную облачность, были видны в радиусе до 1000 километров. Столба составлял около 10 километров. В это же время с самолета, находившегося в 250 километрах от точки взрыва, был виден огненный купол из раскаленных продуктов взрыва. Он медленно поднимался вверх, увеличиваясь в объеме. Максимальный диаметр купола доходил до 20 километров. Пронизав несколько слоев сплошной облачности, огненный купол через 40 секунд после взрыва достиг высоты 30 километров. С этого момента началось постепенное превращение купола в грибообразное облако. Увеличиваясь в размерах, облако медленно поднималось вверх. В своем конечном развитии оно достигло высоты 60-65 километров. Его диаметр равнялся 90 километров. В дальнейшем облако начало утрачивать грибообразность. В этот период диаметр его основания был равен 70 километрам, а диаметр ножки 26-28 километров. При возвращении на аэродром экипаж самолета-носителя наблюдал облако взрыва с расстояния 800 километров. Через несколько часов после взрыва опытное поле вылетел вертолет радиационной ракеты. В район опытного поля вышли корабли испытательских групп. Вот и вот. Через катавки вертолета поверхность радиоактивности. Даже в самом центре площадки она оказалась незначительной. Испытательским группам полигона разрешен был доступ. Вспомним, как выглядело опытное поле до взрыва. Теперь его вид на десятки километров вокруг раскаленная взрывом земля. Разбиты входы в подземные приборные сооружения. На основе даже самых предварительных данных стало очевидно, что произведенный взрыв является рекордным по своей силе. Вместе с тем выбранная высота и метеорологические условия в момент взрыва несколько раз уменьшили предполагаемую зону воздействия ударной волны. В эту зону входил ряд населенных пунктов. Ни в одном из них не было отмечено существенных последствий взрыва. В то же время даже наиболее отдаленных от опытного поля пунктов были отчетливо видны вспышки взрыва, длительное свечение и был слышен звук происходящих ударных волн. Вся регистрирующая зрительная аппаратура на опытном поле сработала нормально. Полученные данные позволили определить фактическую мощность взрыва, характер ядерной реакции, точность срабатывания автоматики изделия и ряд других факторов. Испытание особо мощного водородного заряда, имеющего ряд новых конструктивных особенностей, подтвердило, что Советский Союз имеет в своем распоряжении термоядерное оружие мощностью 50, 100 и более мегатонн.
100 years ago, Democritus said, sweetness, bitterness, warmth, cold, and color are only appearances. In truth, nothing exists but atoms and the void. Ever since the beginning of history, lonely men have searched for a pot of gold under a distant rainbow. Now the prospector has become, in a sense, a scientist. Now the object of the search is not only gold, silver, and copper, but also uranium, radioactive metal which signifies its presence by the reading on a Geiger counter. Scientists foresee that in future years, uranium may supply power to heat our homes, drive our cities, and engineers' dreams, a future reality. Today, nuclear. Atomic power will require years to develop and apply. But atomic energy has still another aspect. The nuclear reactor, incubator of plutonium, precursor of the atomic power plant of the future, is also the source of radioactive materials known as radioisotopes, available now as peacetime weapons in the continuing struggle for health, material satisfaction, and scientific life. The radioisotope is probably the most important new means of perception and investigation since the invention of the microscope. To use this new means of perception, the scientist has been forced to acquire many novel techniques, absorb a variety of concepts unfamiliar to him. Radioisotope becomes useful to the scientist only when these concepts have taken their places in an orderly structure of method and underlying theory. The first concepts the scientist faces are those which have to do with the nature of matter and the dynamics of its smaller components. Now it is known that the atom, long considered the basic unit of matter, is itself a void, in which planetary particles called electrons revolve in great orbits around a central nucleus. The nucleus also has a structure. It is composed of protons and neutrons. Each proton has a weight of 1.00758 atomic mass. The neutron is slightly heavier. In the usual notation, the mass is shown in round numbers, one for both proton and neutron. The proton carries 1 unit of positive charge, indicated in subscript. The neutron has no charge. The electron has 1 unit of negative charge. Its mass is insignificant compared to that of a proton or neutron. Again, charge is shown in subscript, mass in superscript. In describing an atom, the same notation is followed. The atomic number of the element, in subscript, is equal to the number of electrical charges carried by the protons in the nucleus. The mass number in superscript is equal to the sum of protons and neutrons. For instance, designation for helium is 2 helium-4. Normally, the positive charge of the 2 protons in the nucleus is balanced by the negative charges of an equal number of orbital electrons. Atoms can be classified according to the number of protons in the nucleus, or the atomic number, and according to the number of neutrons. In terms of proton number and neutron number, it is possible to define any atom. Normal hydrogen atoms, for instance, have 1 proton and no neutron. Helium, with 2 protons, usually has 2 neutrons. Lithium most often has 3 protons and 4 neutrons, and so forth. All the other atoms are identified according to the same system. The number of protons, or the atomic number, identifies
same element, alike chemically, differing only in the number of neutrons. The sum of protons and neutrons gives the mass number. For instance, an atom of helium, which has 2 protons and 2 neutrons, has a mass of 4. A lithium atom, with 3 protons and 3 neutrons, has 6 mass units, and so on. Different isotopes of the same element have different mass numbers, since they have a different number of neutrons. Again, to complete the description of each atom, the element is accompanied by its atomic number in substance. Most elements have 2 or more isotopes. However, a few have only 1. For instance, cobalt, element number 27, has only 1 natural isotope. All cobalt atoms found in nature have the same atomic weight, 59. Therefore, the same number of neutrons. However, most elements have more than 1 natural form. For instance, zinc, number 30 on the chart, has 5 natural isotopes. Zinc, as in most elements, the number of neutrons is greater than the number of protons. The number of neutrons can be found by subtracting the proton number from the mass number. Higher on the chart, a few additional elements have only 1 isotope, though most have several. At higher atomic numbers, the ratio of neutrons to protons becomes greater and greater. The natural isotopes of mercury, for instance, the lightest atoms have 116 neutrons, 36 more neutrons than protons. The heaviest have 124 neutrons, 44 more neutrons than protons. To illustrate neutron-proton ratio, the isotopes can be plotted on a graph of atomic number against neutron number. In this graph, a straight diagonal line would intersect all points at which proton number equals neutron number. However, if the isotopes found in nature are plotted on such a graph, it is found that they depart from the diagonal. In other words, they have a preponderance of neutrons over protons, a preponderance which tends to increase at higher atomic numbers. With a few exceptions, these positions represent atoms with stable neutron-proton ratio, capable of existing indefinitely without any observable change. The empty spaces represent neutron-proton ratio, which would not be stable. It is reasonable to assume that if an atom existed in an empty space on the chart, it would show a tendency to change itself to an atom having a more stable neutron-proton ratio. For instance, an atom occupying a position above the natural isotope would have a disproportionately high ratio of protons to neutrons, and would tend toward the position of one of the naturally stable isotopes below it. Similarly, an atom having a disproportionate excess of neutrons over protons would tend to take a position of one of the naturally stable isotopes above it. This illustrates one of the primary principles of nuclear stability, the tendency of all atoms to reach an equilibrium in terms of a stable neutron-proton ratio. Up to atomic number 83, the natural isotopes are stable, with a few exceptions. However, above atomic number 83, all the isotopes are unstable. They all have a disproportionate number of neutrons, either too many or too few. Without exception, these isotopes are radioactive and return to stability through a process known as radioactive decay. For example, uranium, the heaviest element found in nature in significant amounts, has 3 natural isotopes. Each uranium isotope tends to return to stability through a series of transformations ending in a stable form of lead. An example of this process is the way in which uranium-238 changes to lead-206. Transformation from instability to stability is a complex nuclear particle of 4 mass units composed of 2 protons and 2 neutrons. This single unit is known as an alpha particle. With this change, the uranium-238 atom becomes thorium-234, which has 2 less units of charge on the nucleus and 4 less units of mass. The nucleus of the thorium atom emits an electron, which possesses a negative unit of charge and negligible mass. This electron, thrown off by the nucleus of the thorium atom, is known as a beta particle, and is usually represented by the Greek letter beta. For this emission of a negatively charged beta particle, thorium-234 in turn changes to protoactinium-234, an atom with 91 charges instead of 90 on the nucleus. Protoactinium-234 throws off the beta particle, increasing atomic number by 1, thus changing to uranium-234. Uranium-234 next throws off an alpha particle to become thorium-230. In successive transformations, further alpha particles are given off, resulting in radium-226, radon-222, polonium-218, and finally lead-240, an unstable isotope. 2 beta particles are emitted successively, producing bismuth-214 and polonium-214. Polonium-214 gives off another alpha particle to produce lead-210, still unstable. Again, 1 beta particle is emitted in each of 2 changes, to form polonium-210. With the emission of a final alpha particle, polonium-210 goes to lead-206, a stable isotope. Thus, in radioactive decay, a complex series of nuclear transformations has taken place from an unstable neutron-proton ratio to a stable state. In every step of radioactive decay, the transformation is from parent to daughter, and parent to daughter. Atoms of the parent element decaying to produce atoms of a daughter element. The same terminology applies whether or not the transformation is to a higher or lower atomic number. There is no way of foretelling when any particular unstable nucleus will decay from one step to the next. However, in any sample of a radioactive isotope having billions of billions of atoms, some of the atoms are always in the process of decay. The number of atoms decaying in a unit time of the sample of radioactive isotope is called the activity of that sample. Activity, or rate of decay, is generally stated in terms of millicuries, or MC for short. A given sample of radioactive material is said to have an activity of 1 millicurie when 37 million atoms decay or disintegrate per second. Millicurie is the commonly accepted measure of radioactivity. Decay from a parent isotope to a daughter isotope can therefore be illustrated in terms of the number of unstable atoms and the time. On this graph, the number of unstable parent atoms that exist at any given instant can be represented by a point. Since the parent substance is decaying, fewer unstable parent atoms will be present at any later. In the language of simple calculus, the number of parent atoms has decreased by delta n during a time interval delta t. The slope of the line between the 2 points corresponds to the rate of decay. The rate of decay, delta n over delta t, is proportional to n, the number of parent atoms present, or equal to minus lambda n. The minus sign indicates that n decreases with time. Lambda is called the decay constant, and is characteristic of the particular parent radioisotope. is derived, which is the basic standard formula for radioactive decay. In this formula, N is the number of radioactive parent atoms present at a given time. N sub 0 is the number of radioactive parent atoms at the beginning of the first time. E is the base of the natural logarithm. Lambda, of course, is the decay constant of the parent substance. Since the number is proportional to the activity, the symbol N can be replaced by A throughout the formula. Accordingly, the same curve can equally well represent the change of activity rather than number versus time. From this equation for radioactive decay, activity at any moment can be determined in terms of the initial activity. In any decay process, there is a point in time at which activity is equal to 1/2 of that present initially. This time during which activity has decreased by half is known as the half-life. In successive half-lives, activity continues to decrease by successive halves, until finally only a small fraction of the original activity remains. Since the decay rate for a specific radioisotope is usually given in terms of half-life, it is often convenient to substitute half-life for the decay constant lambda. The equivalent of lambda is 0.693 divided by half-life. This formula is often used in finding activity at any time t when half-life is known. Plotted in terms of the logarithm of activity against time, exponential decay is shown as a straight line. Figures for half-life are generally available in isotope literature. Each radioisotope has a specific half-life. The half-life may vary greatly, from a fraction of a second to thousands or billions of years. For instance, one isotope of cadmium has a half-life of 2.3 days. While carbon-14 decays to its daughter nitrogen after a half-life of roughly 5,700 years. Or take the case of uranium. U-238 has a half-life of 4.5 billion years, giving a straight line on a graph calibrated in terms of days or weeks. In contrast to the long half-life of U-238, thorium-234, the daughter of U-238, has a half-life of 24.1 days. Thus, while all steps of decay are unpredictable in a single atom, the statistical rate of decay in a large number of atoms can be predicted and measured with great accuracy. Examining the various steps in the decay series beginning with U-238, it appears that there are at least two ways in which unstable atoms can change to a more stable form. By throwing off an alpha particle and losing 4 units of mass and 2 electrical charges, or by throwing off a beta particle and increasing atomic number by 1. In the process of decay of U-238 to stable lead, each of the 2 types of transformation occurs several times. In 8 steps of decay, 8 alpha particles are given off. 6 beta particles are emitted. One would assume that these 14 particles would account for the mass difference between uranium-238 and lead-206. Let's check this assumption. The exact weight of an alpha particle is known from accurate determination. The 8 alpha particles thrown off weigh 32.022 units of mass. The mass of beta particles is also known with great accuracy. Adding the weight, it is found that 32.025 units of total mass have been given off as discrete particles during the decay process. But if the weight of lead-206 is subtracted from that of uranium-238, we find that the total mass lost in the decay is somewhat greater than that represented by the alpha and beta particles thrown off. In other words, 0.045 units of mass are unaccounted for, representing a minute fraction of a gram. According to Einstein's formula, energy and mass are equivalent. Substituting and solving the formula, it is found that this mass represents a really significant energy. In the transition from uranium to lead, this energy has been released in addition to the alpha and beta particles in it. Most of this energy, released during uranium decay, has been applied in giving the ejected particles their high speed. In other words, as kinetic energy. Additional energy is also released as a form of electromagnetic energy known as gamma radiation. To summarize, the decay of uranium-238, resulting in stable lead, is accompanied by the release of alpha particles, beta particles, and gamma radiation. This is generally true. A change from instability to stability is accompanied by energy released as discrete particles or electromagnetic radiation, or both. It is the energy released by the decay of uranium in uranium-bearing ore which makes it possible to detect it with a Geiger counter, even though mixed in minute proportions with a variety of other substances. The decay series, beginning with uranium-238, is only one of several. A similar decay scheme begins with U-235, another with thorium-230, another with thorium-232. Uranium and all the unstable elements near it on the chart have very long half-lives, which have permitted them to survive from an early age of greater radioactivity. They are fated by the inevitable process of decay to return in time to a stable state. Lower on the scale of elements are found a few unstable survivors. Naturally radioactive isotopes of long half-life, such as rhenium-187, lutetium-176, tin-124, rubidium-87, and potassium-40. All of these return to stability in a single step. Potassium-40 offers a good illustration of the three possible modes of nuclear transformation. As one possibility, potassium-40 may give off a beta particle, increasing its nuclear charge by 1 and changing to calcium-40. In this case, the beta particle is accompanied by excess energy as a gamma ray. Or potassium-40 might emit a positive electron, reducing atomic number to become argon-40. The positive electron is known as a positron. As the third possibility, the potassium nucleus may absorb an electron, becoming argon-40 without emitting any discrete particles. In all three cases, there is a change in atomic number without any significant change in mass. The sum of neutrons plus protons remains the same. Obviously, each change must involve a shift in the neutron-proton ratio in the nucleus. For example, when potassium-40 changes to calcium-40, one of the neutrons in its nucleus has become a proton and an electron. In other words, a neutron of zero charge in one mass unit has become a proton of positive charge and mass 1, and an electron of one negative charge and very slight mass. mass and charge units are conserved in the transition. When potassium-40 emits a positron and changes to argon-40, a proton in the nucleus has changed to form a neutron and a positron. This type of nuclear change is called positron decay. In the third possibility, one of the protons in the nucleus may join with an electron to form a neutron. This transformation would seem contrary to logic, since it is generally assumed that there are no free electrons in the nucleus. Such a phenomenon can best be explained by referring to the nucleus and its surrounding electrons. It sometimes occurs that an electron from the inner, or K shell, is captured by the nucleus and is immediately absorbed by a proton. The opposite electrical charges neutralize one another, and the proton becomes a neutron. This transformation is known as K-electron capture. When it occurs, it causes a series of changes in the outer electron shell. First, the empty space in the K orbit is filled by an electron from an outer orbit. The empty space in the second orbit is filled by an electron from an orbit further out, and so forth. In this cascade of electrons from outer to inner orbit, X-rays are released, which represent the difference in potential energy between different electron shells of the daughter atom. The K X-ray, which corresponds to the energy release capture of the K electron, represents most of the measurable energy release. Thus, when potassium-40 captures the K electron and changes to argon-40, the transformation is accompanied by the emission of X radiation. While a single atom of potassium-40 can decay in only one of three ways, with a large number of potassium-40 atoms present, some will decay in each way. Energy is released as positrons, beta particles, and gamma rays, and in K capture as X-rays. In potassium-40 decay, positron emission is difficult to substantiate, occurring rarely, if at all. In K capture, the X-rays emitted are of low energy, difficult to measure. In other radioisotopes, any of these radiations may be given off in different proportions and relative energy. Decay and emission of energy as radiation occurs in all radioisotopes. However, uranium-235 and one or two other radioisotopes have a second and unique characteristic. If it were possible to observe a single atom of uranium-235 and to penetrate through the electron shells to the nucleus itself, it would appear to be in a constant state of agitation. In all probability, it would throw off an alpha particle as the first step in the decay process. However, in a gram of U-235 in each second, at least one atom behaves quite differently. It becomes more and more unstable until it splits into two fragments, each a lighter atom of lower atomic number. In addition, two or more neutrons are left over from the reaction. This is the reaction of spontaneous fission. In a single fission, taking place in a minute fraction of a second,
considerable energy is released, about 4 times as much as in all steps of the long decay process of U-238 with stable lead. Part of the energy is kinetic energy, giving velocity to the neutrons in the 2 fragments of uranium. The remainder of the energy is given off as gamma radiation and beta radiation. In uranium fission, 1 to 3 neutrons are emitted. If enough uranium atoms are present, one of the neutrons may strike and be absorbed by another nucleus of U-235. With the added mass, this nucleus in turn fissions, releasing still other neutrons, and the process continues. This is a chain reaction, such as that which takes place in an uncontrolled manner in the atomic bomb. However, if uranium fission occurs in uranium mixed with some light substance, such as graphite, the neutrons are slowed down by collision with the carbon atom. Because of its slowing action on the neutron, the graphite or other light substance is known as a moderator. The neutrons, because of their reduced velocity, are much less likely to escape from the uranium and are much more likely to penetrate the nuclei of the uranium atoms. If the faces of the blade are tapered in slightly, a short distance back of the tip, the screwdriver will stay down in the screw slot, even when a severe twisting force is exerted. Here is a special type screwdriver designed for heavy duty. The extra-large square shank will stand a wrench if added leverage is needed. Don't be a primitive, Pete, and resort to the use of pliers.
that precious water from draining away into the outside main. Turn on the faucet located at the highest point in the building to let some air into the system. Then, drain water as needed from the lowest point. Don't forget sanitation supply. A metal container with a tight lid for an emergency toilet and toilet tissue. A garbage can for wastes. Plastic liners and disinfectants. Medicines and first aid supplies. Blankets and bedding. Extra clothing and underwear. Soap, towels, personal hygiene items. Flashlight and candles. Fire extinguisher and buckets of sand. And a battery-powered radio with extra batteries so you can receive news and official instructions. If you're going to a public fallout shelter, bring as much water and ready-to-eat food as possible. Extra clothing, blankets, a flashlight, special medicine, and personal hygiene items. If you're being moved to safety from a high-risk area, pack emergency necessities of your family things to go on a trip. Plus blankets, bedding, special medicine. For your own protection, remember 3 basic things. First, the attack warning signal. A 3 to 5 minute wavering sound on the sirens. Or short blasts on whistles or horns. Next, the effects of a nuclear explosion. A blinding flash. The heat wave. Then the following blast wave. And finally, radioactive fallout. Remember your 3 defenses against fallout. Mass. Thick, heavy, dense materials to shield you from the radiation from fallout. Distance. The farther you are from the fallout, settled on the roof and the ground, the safer you'll be. And time. Radioactivity does weaken rapidly. With shelter, you can wait it out. Take a battery-powered radio with you and tune to your local emergency broadcast station. They'll tell you when safety come out. Don't forget spare batteries for your radio. Remember, too, that you have 3 choices. 1. Go to a public fallout shelter. Know where the nearest one is. Your office, your home, your children's school. Be prepared to take along food, water, the other necessities we mentioned. If you decide to take shelter at home, know how to improvise and improve your protection there. And do lay in enough supplies. Relocation. If you live in a high-risk area, your local authorities may ask you to move to safety in the small town or rural areas. Be sure you know their emergency plan, so you'll know exactly where to go and what to do. Whatever the choice, take time now to make your own family protection plan. Know what you'll need. Make your plan practical. And make sure each member of the family knows exactly what to do if crisis ever comes. Don't wait till you need it. That's too late. Do it now.
The Earth from space can seem a fair and pleasant place. And perhaps through strength and unceasing efforts to settle international
chances of survival will be much greater if you remember these facts about protection in the nuclear age.
preparations made, maker shots occurred on schedule. Many impressive and startling effects were observed on this shot, including the first appearance of a base turbine, seen here enveloping the target ship. April 1948, Eniwetok is called from Pacific. Our third nuclear test program gets underway. Operation Standstill. 3 weapons, fired on 200-foot pounds, with batteries and scientific instruments to record results. As it proceeds, drone planes are used here. Giant planes, heavily instrumented, but without crew, take off to fly through the heart of each atomic cloud, to collect samples of that cloud for detailed radiochemical analysis. Three times the sound and fury of atomic detonation shattered the Pacific dawn. 3 times a scientific laboratory was created to study previously unattainable effects of high temperature and pressure. But what did we learn from these detonations? What were we trying to prove? Why did we expend this almost priceless nuclear material and these thousands of man-hours of labor? Let the men of Los Alamos give us the answer.
We returned to the hill from the sandstone test with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, chip design, core arrangement, initiators. Information that would enable us to increase the small percentage of active material actually burned during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive or elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive source, and that the implosion principle was found. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonation, the effects from an atomic explosion became of prime concern to the armed forces. Thus, Crossroads using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Cable and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory research in the meantime developed new weapons with the sandstone test. At Sandstone, we were once again able to tackle the big problem, more efficient use of fissile material. Here we were able to utilize uranium-235 in an implosion-type weapon. As time went on, we had increased our knowledge of weapon design and had, therefore, increased joule per kilogram of active material. This is where we stood by the end of Sandstone. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as Day Division, is organized. Dr. Alvin C. Graves was selected to head this division, a unit with the specific job of testing weapons. By autumn of a test program is framed. This calls for experimentation of new weapon design with the objective of again moving our knowledge curve upward to a more effective level. Once more, we propose to better yield per kilogram invested. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon. These are the main objectives in the weapon development field.
So Operation Greenhouse gets underway, with Enewetak designated as expert on Pacific Proving Ground. Entity, and the rule of the top. During late 1950 and early 1951, work progresses in the Army. Towers are built. Recording stations are constructed. Coaxial cables to the dock towers are laid. Myriads of instruments, instant wiring hookups are checked and double-checked. Finally, everything is ready for the biggest job in nuclear testing. The job of obtaining exact information about the detonation itself. The builders are through, and the scientists take over the story.
Those of us in the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into two major areas, diagnostic testing and effective testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of an explosion. Effective tests study the external manifestations of the explosion, the effect of the weapon. To gain an intimate understanding of interior weapon behavior, three kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time, the rate at which the chain reaction multiplies, alpha measurement, and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of the nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HV system, is cabled down to a recording station and measured by sleep oscilloscope. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between the impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomenon. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fission in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons. 1 kiloton being the force released in 1,000 tons of high explosives. One means of measuring mules is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield for fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shot time. They will travel in a long arc and pass through the clouds at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself.
Dot number 1, draw. The objective of the test of the foul weapon is to prove the weapon of higher yield and efficiency than currently stockpiled. The predicted increase of efficiency made possible by the tight speed test was confirmed. Dot number 2, easy. The objective of the test was to prove a lighter and smaller weapon with acceptable efficiency. The feasibility of obtaining acceptable efficiencies with lighter and smaller weapons was confirmed, and thereby future weapons design was advanced. Dot number 3, yours. A step was taken along the path to thermonuclear weapons by the achievement of a fusion reaction. Dot number 4, isotope. The successful booster reaction proved the feasibility of increasing fission yield by a limited fusion reaction and gave more impetus to the development of booster weapons. Fission weapons proof testing, physics experiments run on thermonuclear reactions, military and civil defense knowledge immeasurably increased. This was the accomplishment of Dominic and entity at evolution in the spring of 1951. Once more, Pacific Proving Ground has proved its value, but the job is far from complete. Each test series leads inevitably to new developments requiring still more tests, more frequent than are practical at distance and a recon, where logistic problems make it difficult to run more than one test a year. We need a site much closer to home, a site in the continental United States. But where?
For a long time, as a matter of fact, ever since Trinity, men from Los Alamos had been eyeing the great barren stretches of the Southwest. This region, for the most part, fits the bill. Isolated from centers of population, with favorable winds, with the necessary consistency of soil and formation of earth strata below, and so beyond the
underground detonation. Like the surface, this will be a 1 kiloton gas, but this time it will be detonated 17 feet beneath the surface of the Nevada soil. Very extensive military effect tests will be run with this detonation. Dummy buildings, superimposed loads to represent upper floor, an underground structure, such as fuel storage tank, water systems under hydrostatic pressure, gas mains, and electrical mains have been constructed to gain realistic data on ground shock and cratering action. Inside the control point, members of the military effects test group supervise the detonation.
5, 4, 3, 2, 1, 0.
After the detonation, test structures are studied, and the many scientific and military personnel involved return to their home bases to evaluate the results of the operation. After the sudden shock plus the jangle, the test area lies dormant, waiting, ever ready for future tests. Our proving grounds, Enowetok and Nevada, stand ready to aid the scientists and the military in their job of